Hello, I'm Professor Ira Pohl from the Baskin School of Engineering at the University of California, Santa Cruz. Something about this course interested you, and now you're watching the first video. Let me explain why you should keep going and what you're going to learn. First off, why code? Coding is now a universal skill. I think coding should be added to the curriculum even at the high school level. It should go along with reading, writing, and arithmetic. This is the new world. In the new world, we want to understand how to properly express algorithms that can run on a computer. And this is absolutely a critical skill you're going to be using in the new world. Why this course? Well, probably the best reason is I've designed this course for everyone. If you're an aspiring computer scientist, you will benefit. You'll get a rigorous introduction to concepts such as syntax and operator precedence, and then you'll be able to move on to something like more advanced programming. Indeed, on Coursera, I already have a successful two-part C++ for C programmers course. On the other hand, if you're another kind of scientist, a biologist or a chemist or an ecologist, then you want to be able to code all sorts of functions so that you can model scientific theories. Again, crucial to pursuing any part of modern science. Finally, if you're a humanist, you're going to learn how algorithms work, and you're going to be able to do things like get the computer to write poetry. So this is for everyone. Everyone will have an opportunity to work on a problem that comes from a domain that motivates them. And the essential skills, such as understanding how to write a loop, will be universally taught, but then you'll be able to practice in an environment in which you're comfortable, in a problem-solving environment appropriate to your background and your interests. Okay, why the coding language C and not Java or Python or Pascal? There are many, many introductory courses for these other languages. These other languages are in many ways very suitable for teaching beginning programming. And there's nothing wrong with starting with another language or coming over from another language. But even if you've had a start in Python or Java, you'll appreciate learning C. C was invented by Dennis Ritchie at Bell Labs in 1972, and it's a tried-and-true language used throughout industry. It's what's called a systems implementation language, a SIL. With my approach to C, you're going to learn low-level details. A lot of these other languages, like Java or Python, hide some of these details, which partly makes it easier. But then, if you want to move on and learn more or understand at a deeper level what is being done by the computer, you need to be able to program or code in a language like C, which is near the bare metal, near the computer, and gives you that level of understanding. Okay, then, I think you're going to keep going with this course. You'll have detailed video lectures in which I demonstrate the principles and procedures of C. You'll have segments from a book on C, which I wrote with Al Kelly. You'll be able to check your understanding with regular quiz questions. There are peer-reviewed programming assignments where you can demonstrate your new skills and see what your fellow learners are doing. And I hope you'll be active in the discussion forums. I'm looking forward to seeing what all of you, whether you had a lot of experience or none at all, will learn to do with C. We're going to talk about the origins of the C programming language. The language was invented by Dennis Ritchie. Dennis Ritchie invented it in 1972. Its purpose was to write an operating system. The operating system became so famous that we're still using it. It's called Unix. And while it was research, which he conducted with Ken Thompson, because it was done at Bell Labs at that time, it was released as a free product. So people who wanted to use an effective, at the time, small time-sharing system, or a system that let you have multi-users on a small computer, had many advantages. And it was just the era of the mini computer was just starting. So people who had very large computers, like millions of dollars of big hardware from IBM or Burroughs, this wasn't how they were going to use their computer typically. Instead, this was for computers just being developed by places like Hewlett-Packard and then Digital Equipment. Later, the system becomes very important because it could also be used on small personal computers. And indeed, it's the basis of Linux, and it's the under the hood mechanism behind the Macintosh operating system. Very important. In fact, so important, both Ritchie and Thompson won the highest award in computer science, which is called the Turing Award. Okay, we need to talk about the tools you'll need to learn C programming. And the basic tools you'll need, whatever your operating system is a compiler, a C compiler, and an editor. And the simpler editor is better, an editor that's a plain text editor. You can, of course, use something like Microsoft Word, provided that you store things in plain text. Microsoft Word is an intelligent editor. It adds all sorts of funky characters. A C compiler doesn't expect that, and so that would confuse it a lot. So if you're going to work on something like Windows, you can use typically a compiler like Notepad. Okay. What are the tools? A tool, for example, that's a C compiler that's freely available and generally can be installed on most any computer system, is the GNU compiler. The GNU compiler has as its command GCC, or, of course, the other major system you're likely to be on is Windows system, and there you can get very good tools directly from Microsoft, and they're probably the best tool would be a form of Visual Studios. Okay. Now, what I'm not going to do in this class is go into detail about different compilers, little nuances for the compiler, how to install the compiler. All of these things are required. In many cases, the install procedure is no more complicated than getting a package and just following the instructions that typically will install what you need. But if that's not your level of expertise and you're uncomfortable with that, you should get some help. So the presumption here is you have a C compiler and you have an editor. Again, I'm going to use a universal editor. It's freely available. It's sometimes called VI or VIM. As I said, an alternate editor for a Windows system might be Notepad. And what you'll see throughout this course is my home computer, which is a Mac, and I'll be using the Mac with its terminal window. Why the terminal window? Because that's a very simple programming environment. It's very vanilla. It's basically the Unix operating system. So some of you may even have a Unix operating system, either through your university or sitting on whatever box you have. And there are Unix operating systems that can sit under Windows, as well as the already installed one for a Macintosh. And what we will use is VI, and VI will be used to write code or data files. And the instructions that we need to use there are fairly simple, but again, it's not the point of the course, and so you should get comfortable with how to use a basic, simple text editor. Again, in this window, we will use the GNU compiler and the GNU command GCC to compile our code. And when you get an idea to write code for a particular problem or something you're interested in, or some test, I always say write the code first on paper. Paper and pencil, maybe I'm just old school, lets you think about it, and even what we call hand simulated. So not only do you write it, make sure visually it looks like what you think it is, it looks like a correct or syntactically correct C program, and then go through it, step through it, or at least a simple version of it, and see that it gives you the result you expect. You might even start with some sample program that you'll modify, and here's a very simple sample program. It's just int main void curly brace, return 0, semicolon. And when you're finished writing that code in an editor, so I've already written it on paper, I then go and open my editor. My editor command in this case would be VI. I would say VI of sample.c. And typically when I'm writing code for a C compiler, I have a suffix .c that indicates to the compiler that this is C code. And also if it sits in a folder or in a directory, I can recognize it as being source, what we call source C code. Then I'm going to actually make sure the program works as I thought. So we'll call in our GCC compiler. We'll see if there are any syntax errors. When we fix all the syntax errors, we can recompile. The fix is going to have to require use of the editor again. We keep running the program. We either get wrong answers, we go back here, fix, recompile, run, and then finally we should get a behavior we like. That's correct. And then in the GNU compiler, you'll see an output file automatically show up, which is your runtime executable code. You can think of that as machine code. And that file is by default a.out. And the problem with having a.out as your executable is anytime you use the C compiler, that a.out will be replaced if you have compiled a correct C program. So in order to avoid that, you can either change this by moving it to something recognizable, for example, sample exe, or you can do this from scratch by using the GNU command -o, means compile sample.c, and then the output should be in sample.exe. And now we're going to actually go over, and in the next segment, show me doing all this on my Macintosh environment. Okay, as promised in the last segment, we're in my directory. My prompt for my computer is Ira's Air, : and the local directory that I'm running in is called cprogram/week1. So here's where I develop some of the code that was being used in week 1 of this class. So let's look at that directory. The way we can see that directory, again, we're in terminal for a Macintosh, terminal window, which is basically running Unix. So I can use Unix commands. The Unix command ls shows me the files in that directory. So we see there's an a.out file, there's something called add2.exe, and then there are these .c files, which are source files, which are code, and then we can see something like miles.exe, circle.exe, add2.exe. So all of that are what I previously compiled into an executable, and I can, of course, execute them. Let's look at add2.exe. So in order to execute them, all I have to do is say add2.exe. It says input 2 floats. I do that, and I'm done. 4.3 and 6.8 is 11.1. Now, if I want to develop a program, let's say I want to change the input 2 floats program to an input 3 floats. Let me try doing that. So I'm going to have add3. I'm going to call it add3.c. vi add3.c. So this command means create a file called add3.c. Now, it's going to look very much like add2.c. So basically, and frequently the case is, I'm going to want to modify a pre-existing file. So I'll just read that file in. And these are all VI commands. And again, in this class, I'm not going to go through all of the VI commands or notepad commands. You're just going to have to get comfortable with using an editor. An editor is a critical tool for almost anything on a computer. And once you understand a little of it, you can get a tutorial that explains in detail the editing commands you need. So, okay. I mistitled that file, so I couldn't read it. There it is. Read in 2 floats. So here's a classic kind of thing. Let's change it to 3. So that was a CW that I printed, and that means change word. And I'm going to change the word to 3. Okay, today is not the 18th, it's the 19th. I'll change that. Again, I might have a sample program of some kind, and it's just always going to probably include standard I/O. And so I don't have to always be redoing my program. I have something standard. Now, indeed, if you go to an environment in Windows with something like an IDE, more elaborate IDE, like Visual Studios, it'll probably give you a basic template for starting such a program. So an integrated development environment like Visual Studios, once you get the hang of it, though, it's got so much stuff in it that can be intimidating, does give you a leg up on doing programs. It gives you a lot of additional assistance. So instead of float AB, we need a third. I'm going to just do an addition here. So I'm going to also have a C, comma. Okay. So little a says add at this place. It's a way to do an insert. And here I'm going to say input 3 floats. And I'm going to make an error here because I want to show you the whole cycle. So let's make an error. Instead of, I'll hit the wrong quote sign. So many places in a C program, we have to have matching braces, parentheses, all sorts of things have to match. Here I'm going to get a third float. I'm going to print the third float. I'm going to do an insert. That's another way to add immediately. So that'll be C equals %F. Oh, and here I'm going to also make a mistake. I'm not going to put C in. So it's expecting 3 values, but it's only going to display 2 values. What's going to happen there? Again, we're going to see how the compile edit cycle works. All right, so I'm done now, and I'm done, and I can exit, and I can do a colon, right? I can do a colon quit, and I can try to compile now. So I'm ready for the next phase, which is to call the compiler. I'm going to use this .o to say that I want that to be add3.exe if it works, and add3.c is my file to compile. Whoops, warning, missing terminal quote, invalid. And it even shows it. This is not being matched. So that's pretty good. And then it says error, makes a number of other errors because there's confusion about matching. So let me re-enter that editor. I used a shortcut. I just said !V, which means use the previous editor command. Let's go and correct this error. I pointed it and even told me what line it was on. So I'm going to try and redo this, and I'm going to go ahead and also okay, 1 warning and 2 errors generated. It said a warning. There was more conversions than arguments. That's not a syntax error in itself. It's something where the compiler's intelligent enough to show that something did not make sense. But the warning didn't allow me, I believe, to still go ahead and build an executable. And this says input 3 floats. 3, 4.5, 6.6. And look what happened here. I got 3, 4.5, but C was shown as 0. But the right result happened, 6.6, and we ended up with a sum of 14.1. So if we had fixed the program based on that warning, and I'm going to go back and do that, we wouldn't have get that funky C equals 0, because C equals 0 was the initialized value of this float but it wasn't changed by the scanf, because it was changed by the scanf, but it didn't show up in the printf, because here it said %f and there was nothing to read out of. So here we're going to now correct that. Okay, I think I corrected it. Let me recompile. Okay, no warnings, no errors, everything looks okay. Let's try the add 3 again. Input 3 floats, 1.1, 2.2, 3.3. That should be, what, 6.6, I hope. Sure enough, done. So we've seen how we get syntax errors, how the compile cycle works, how we run, recompile, make our fixes, and finally get working executable. And indeed, if we go and look in the directory, there is add3.exe and our program. Okay, so this is my working environment. It may not be yours. You might have a different kind of Unix. This is under the Macintosh, but mostly Unix environments will look like this. Or you might have a totally different environment for Windows, and you'll have to use a different editor and probably a different compiler. Or you can import a new compiler within Windows and use a Windows terminal box as well, if you want to approximate this environment. Or you can again go and use Visual Studios and use one of its simpler project modes to get you here. Okay, so we just talked some about Dennis Ritchie. Let me put up his webpage from the Wikipedia. Okay. We can see Dennis, he was born in 1941, died 2011. Listed as an American computer scientist. He created the C programming language, and with a colleague, Ken Thompson, the Unix operating system. And that's his picture towards the end of his life. And as I mentioned before, he was awarded the Turing Award in '83, which is computer science's equivalent to the Nobel Prize, and he also got a Hamming Medal and a National Medal of Technology. And then another critical thing was he was the R in Kernighan and Ritchie, the C programming language, which was the original Bible for the language. So C was created by Dennis Ritchie. He was working with Ken Thompson at Bell Labs, and this was 1972. And some of the characteristics of the language that make it useful and powerful was it was small, as we'll see. The number of concepts you need to understand to fully learn C is much smaller than current languages. C++ is at least 3 times the size of this language when you use a metric like keywords. Keywords are critical to understanding language. They're reserved for special meanings. We'll talk explicitly about them shortly. It was low level. Low level is used when you need a great deal of efficiency and access to all the machine resources. So its job was to build an operating system, namely the Unix operating system. And that was the joint project of Thompson and Ritchie, where they won the Turing. And then the other thing it was highly efficient. It was easy to translate from C, sometimes C is called a portable assembler, into the actual machine code, regardless of what machine you were running on. C is sometimes referred to as a systems implementation language. And later, it got to be used as a general purpose language, but it was originally used to replace languages like B, its predecessor, and BCPL, which was B's predecessor, which were also being used to implement small operating systems. And they were also critically reliant on the design of Algol 60. Algol 60 was a language codified by an international group of computer scientists in 1960, right at the beginning of where there is computer science. And if you're interested in majoring in computer science or are a computer scientist, I highly recommend for the majors that you go back and look at Algol 60. Many of the concepts that we still are heavily using started with Algol 60. So when we examine C, we're going to see a first program. It was made famous by the Kernighan and Ritchie C programming language, the Bible. And indeed, it's one of the books I recommend, especially if you're a computer scientist, because it's somewhat sophisticated. And while my book, A Book on C, is more didactic, more tutorial, this is a very thin book for people who already understood programming. So it was written for people who knew other programming languages, just to expose them to the C language. And it was written beautifully, largely influenced by the first author, who's an excellent writer, Brian Kernighan. And in that language, in that first program, we see include standardIO.h, which is a library for input-output. Then we see one of these keywords, int, includes a keyword, includes a preprocessor keyword. Int main is always a function that we use. It's where the program begins, and then these brace pairs, well, those are parentheses. Then this is a curly brace. We sometimes indicate that that's the beginning of a piece of code. And then we have this function out of the standard library for I/O where it prints to the screen, printf, quote, this string, hello world, and we have this funny little \n, and that's a silent character. \n means instead of printing something, advance to a new line. And then we also have return 0, which says we're going to finish the program, and a special value 0 is going to be indicated to the operating system, meaning everything has completed correctly. And then we have the closing brace. So one of the things you're going to be exposed to in programming is making sure you have matching braces, making sure you keep to your punctuation. There's matching parentheses. There's matching quotes. There's special the semicolon is heavily used because the semicolon always indicates the end of a statement. So we'll have in our grammar, in the syntax for the language, things like punctuation, which are very important, special characters and punctuation, semicolon being most important, braces being incredibly important, and parentheses. And if we mismatch these, it's not like writing an essay. The compiler immediately basically issues an error and says it won't compile code. Now we're going to look at a program that has both input and output. So again, very critical. We frequently, as a user, we're used to it. Let's say in an app, we're always entering information, and somehow our program or app has to capture that information, and then it makes use of it in delivering a response or a computation. And this is going to be a very simple one that we all know about, which is how to compute the area of a circle. We're going to do that in terms of meters. So let's look at this code again. We're just getting used to how to write a simple C program, some of the elements of it, and later we're going to go into detail again about what each thing is and how it's constructed. So as before, there's our standard program comment, and it's really for readability, and in this case it's telling us this program is to be used for computing area of a circle. Standard I/O, the preprocessor command brings in both printf and now scanf, and scanf is a basic routine for doing input by default. In most cases, we will come from our keyboard. In the very old days, this could have come from a card deck or a paper tape. So it depends what you default. And in our case, standard input is defaulted to the computer keyboard. Here we see another directive. It's called a define directive. The define directive does an interesting thing. We have, and this is by convention, a preprocessor token. In this case, we'll call it pi for obvious reasons. Again, we want this to be documentation. We want to make the program readable. And we will define pi to 6 significant figures because that's what we get to store in the normal double. So it's 3.14159. Again, we introduce the program, which is main. We begin with what's called the open brace for a compound statement. And the first statement is a declaration statement in which we define area and radius. Area and radius are two identifiers. Identifiers can be ordinary words, unless they're keywords like double. So unless they're a keyword, you can make use of whatever you want to think about. And we initialize area to 0 and radius to 0, and we use 0.0 because that's a clear indicator that we're doing constants which are double. We could use 0, and that would be allowed. We then ask the user, please enter a radius. Otherwise, if we just didn't do anything and we had omitted this, and try omitting it, you'll see that your screen stops and you won't know what to do. So this is what we call a prompt. So it prompts the user to enter a radius, and this says enter the radius as a double, long float, and we need this special operator ampersand here. We'll explain that later, but for the moment, trust me, just use ampersand of whatever that variable is. We're going to explain that much later in detail in the course because that's really a parameter that's the address of radius, and we'll have to understand things like address, memory, pointer to really understand what's going on. And here's our area calculation. Everybody should remember that from grade school or high school. pi times radius. We don't have a simple way to say square, so there isn't a notation like star 2. So we use repeated multiplication, and then we print our answer. Return with 0. So let's make sure we can use that program. I've already compiled it. Now I'm going to execute it. So I compiled it into code, circle.exe. It says enter radius. Let's try the radius 1.0. Oh yes, 3.1459. Well, that makes sense. That's a simple test. When we go to debug programs, we want data for which we know the answer, and we want simple cases first. And we can ask for a more complicated case. Let's repeat that. So it's saying enter the radius again. Why don't we do 2.5? In this case, it's 19.634937. And that's correct as well. Okay, so that shows you how not only to do simple output, which we've studied in a few cases, but also simple input. And the little secret there is, outside of using a format string, where you want the input, you have a % with the appropriate format, in this case double, so it's LF. If it was an integer, it would be %D. And then we have to, instead of using the ordinary variable name, we have to use the address of that variable. Okay, so we need more practice with output. Output is a very important component of programming. We know the famous expression, garbage in, garbage out, and it wouldn't be useful in most cases to have programs that don't produce answers, so output is critical. So let's look at a program that's going to convert a marathon distance from miles and yards to kilometers. Here's a program. The distance, marathon, in kilometers. Now again, that first part that I've just highlighted is a comment. A comment is just something that gets thrown away. So why do we have comments if it gets thrown away? Well, we need to make our code readable for a variety of reasons. First off, somebody needs to maintain the program. They have to understand what the program is being used for. What's the history of how the program got developed? So we typically like to put in when the program was last updated or coded and by who, and some overall comment as to the use of the program. Now, the first thing that actually shows up in the C code is what's called a preprocessor command. That's the sharpen include. And inside the angle brackets, we see stdio.h. And the .h is an extension that means a header file. And that means that in this file, which will be included automatically with our program, so it tells, it's called preprocessor because it happens before the C code is compiled. So extra code gets added, and that code is the code that we're going to need for doing printf. Without it, the printf would be undeclared. Then we start the actual code, and that's with the keyword int, which means that the function called main, and almost always, in fact, in our beginning course, everything will always have a main. Main will be where the program executes from. That's understood by the C system. Void is another keyword meaning no arguments. So int is a keyword meaning that the program returns an integer. Void is a keyword that would, if it's used as a data type, means it's an undefined data type, or in this case, it means that the argument list is empty. The next thing we see is this brace. An open brace means begin the code. It's in programming languages, there are a lot of matching braces. We've already seen matching. We've seen the star asterisk match. We've seen the angle brackets match. We've seen the parentheses match. Very critical to getting syntax right is to make sure you don't improperly match braces. So for this brace, there's a closing brace, and this is called a compound statement. It's a series of statements that is the executable code here. We have two simple variables that are integer type, and this is called a declaration, and it's a declaration with initialization. So miles is initialized to 26, yards is initialized to 385. And a good programmer chooses identifier names. Miles and yards are identifiers. Why choose something like that rather than M and Y? M and Y might be okay, but it adds documentation at no cost. So the fact that we use an actual word like miles or yards gives the program more literacy, makes the program more literate. And then the result is going to be, again, a literate identifier, but this time of type double, and it's going to be kilometers. And then the formula is kilometers is assigned 1.609 times miles plus yards divided by 1760.0. I'm going to mention this because it's important and it will be reemphasized later on. The reason that we didn't choose to use 1760 is that yards is an integer. This would be an integer, and if we did this without making this, in effect, a double constant, then this would have given rise to 0. We would have gotten the integer division of yards with 1760. And 385 over 1760, when they both are integer, is 0. So we could do this later. We'll learn that we can also use a cast. Another trick would have been to say 1.00 times yards divide by 1760. And what happens is there's an explicit conversion which takes the more extensive type and makes the whole expression be of that type. And then we have the print statement. And in the print statement, we first have the controlling format expression, which is a string. So again, you see matching quotes. At an earlier time, I left out one of these quotes, and you get a syntax error. So you should see what happens if you leave out one of the matches. You'll see you get very different kind and sometimes obscure syntax errors. But this says, print a new line, which means advance on the screen. A marathon is, this says, use a long float or double format. Print kilometers, period, and then 2 new lines. And then kilometers is, in fact, interpreted and printed as a long float. and then return 0 because we told you that int has a integer value, and so that returns 0, and mysteriously that returns 0 to the operating system. 0 being a code that the program ended correctly. So let's execute this. And indeed, we get a correct result that a marathon is 42.185969 kilometers. Okay. So study this program. It's a little more complicated than the previous program, but it gives you a lot of critical ideas. And we'll go into the various things that were talked about in later lectures in more detail. Okay, the next program we're going to look at is a program that converts from Fahrenheit to Celsius. That's degrees. So remember the Fahrenheit scale, for example, for ice, that's 32 degrees, but Celsius, which is a little more logical, it's in the meter system, and we go from 0, which is ice, to boiling water, which is 100, which in Fahrenheit would be 212. And it's a little hard to do that in your head, so we're going to just write a little program. And the reason we're going to do that program is that it illustrates a number of principles that we find in the C language, and indeed it's one of the early programs. A form of it is an early program in the great classic, the C programming language by Kernighan and Ritchie. And of course, remember, Ritchie is the inventor of the language. And there's a lot to learn, so if you're going to get serious about the C language, it's definitely a book you want to consider on your bookshelf. Now, as before, we're going to do input-output, and the character of the program is we're going to ask you to type in a Fahrenheit temperature, and then the conversion will be to a Celsius temperature. Int main void, of course, main by convention is where we always start our programs, so a C program should always have a main, and technically its type, its return type, is integer. We're going to use, though if we wanted more scientific precision, we might use double, but in this case we're going to use int as the basic type for Fahrenheit and Celsius. And then we're going to be polite on asking for data entry. Please enter your Fahrenheit as an integer. And notice again, for the moment, if you don't fully understand it, the scanf, which gets us input, we have a format that of %d, which is the format for integer, and then we use this fancy symbol called ampersand, and the ampersand means shove it in the address of Fahrenheit. We can't say Fahrenheit without the ampersand because Fahrenheit is a variable, and if we said Fahrenheit, we would look for the value in that variable. In this case, we want to look for the address of that variable. An address is a location in memory. And then here we do the computation. Celsius, it's Fahrenheit minus 32, and it's divided by 1.8. Or equivalently, we could have multiplied by 5/9, and that's a conversion. When I say note conversion, that little comment means that this expression is actually going to be done as a double, because the constant 1.8 is a literal double, even though this is an integer. And then this all gets done as a double and then gets reconverted to an integer. So there are what are called silent conversions going on, and we will have to understand them. They're often confusing for the beginner. Finally, we use a printf, and we have again, in that printf, we have two places where we're going to output integers. So we're going to output an integer, %d of Fahrenheit and %d of Celsius. Both will be integers, and return 0 is just the clear way, even though it could be omitted, that says we finished with main and everything is okay. Let's actually do a conversion. I think I already compiled it. So a dot out. Well, let me just clear the screen. Oop. For example, 32. And that would be 32 Fahrenheit is 0 Celsius. So to see it a little better, I'm going to clear the entire screen. I will run my executable again. Let's see what happens if we do boiling Fahrenheit, boiling water. So that's 100. And if we were to do some random thing in the middle, currently where I'm sitting, it's about 92 degrees Fahrenheit. So Celsius, that would be 33. Okay, that program shows us how to use simple variables, how to compute simple expressions, and how to do input and output. And while it's not exactly the Kernighan and Ritchie program, it is very close. And if you go to Kernighan and Ritchie, what would be added in their version of the program is a little more sophisticated. And we're not ready for that. They do a while loop and print a whole table. Our next program is to compute the distance of a marathon in yards. So it's again a conversion program. Very similar to the program we did where we converted from Fahrenheit to Celsius. But we're going to see a few extra differences, and it's very worthwhile to practice on these programs because some of the very basic things you have to get down, and they easily trip you up later on if you try to do something more complicated. So the idea is we're going to take in miles and yards a marathon distance. You can see it to be 26 miles and 385 yards. And there's a formula. It's kilometers times roughly 1.6 times the miles plus the yards, and the yards is divided by 1760. And that's just a conversion formula we have to get you to kilometers. And then we'll print it. So indeed, if we run this program, I think I pre-compiled it already. And you see a marathon is 42.185969 kilometers. Now, the program we had just seen with Fahrenheit and Celsius, we kept all an integer. That's a rougher consideration. In this case, we wanted a more accurate answer for the marathon. Otherwise, if we had done it all in integer, we would get something like 42 kilometers. And that might be an interesting exercise to check, see what you would do if you did it all as an integer program. See if you would get 42. Now, let's explain some of the ideas we find in this program. This marathon program is taken from a book on C by myself and my co-author Al Kelly. It's one of the early programs, just like the Fahrenheit Celsius program is an early program in Kernighan and Ritchie. And again, if you want to follow this course and you want a lot more detail and lots more exercises, a book on C is one place that you can get a lot more exposure. So there are some differences with the Fahrenheit to Celsius program. Let's look at what they might be. In that program, we had a declaration, int miles equals 26, comma, yards equals 385. That's a declaration with what's called an initializer. So each of those integer variables is given a value, 26 for miles, 385 for yards. Again, that type of statement is a declaration. In the program, we declare the variables we're going to use. We must name them. We want to pick names that are meaningful because that's good for the documentation of the program. It makes it easier to read and maintain and easier for other people to use and modify for their own purposes. So miles and yards were identifiers. Int means that that was the data type those identifiers are allowed to use. And recall that on a normal machine, which is typically a 4-byte machine, where an integer is 4 bytes, you can get roughly plus and minus 2 billion. So if you go outside that range, something's going to go wrong. But if your program only needs the integers and plus and minus 2 billion, you'll be okay. Now, in some machines, you're allowed to go to long int, which might even be much larger. And there's even cases where you can go to long int. But if you need a very large integer range, you have to use special packages. The other key thing to look at in this program is an expression. And that expression, let me get this as full screen. That expression was kilometers is 1.609 times miles plus yards divided by 1760.0. And it's very important that we used 0.0 rather than 1760. And this is one of the key things that can easily trip a non-C programmer up, and certainly a novice. So I didn't write out miles, I didn't write out yards, but I'm condensing this expression and adding parentheses. And those parentheses indicate the order in which the expressions are done. So the first thing that gets done is 7 divided by 1760. And the reason that we were careful about this to be a double is that if we had this as 1760, it would have been an integer divide. But when we make it 1760.0, it's a floating point divide. Now, 235 divided by 1760, if 1760 was an integer, the answer would be 0. But since it's a double, you get an appropriate to something like 6 significant figures expression for that value, a fraction. And we didn't want it 0. Now, once this expression is double, and we do this divide, and we get whatever we get, and then we add in miles, The second thing we've done is now add miles to that. And then finally, we multiply it by 1.609, and that's the third thing that gets done, and that gives us that answer of 42 kilometers and change. So it's very important in your expressions to know what domain you're in. By domain, I mean things like integer and double, because that's going to tell you what the arithmetic is being done in. And that arithmetic can affect the meaning of an operator like divide. Divide can be an integer divide if everything is integer, or it can be a floating point divide if one of the arguments is floating point. And then this answer ends up a double. Okay, so this example gives you a number of other ideas to go with the ideas from the Fahrenheit example. And let me give you a suggested exercise modify the program to input miles and yards. And then it could be a general conversion, much like the Fahrenheit to Celsius, to kilometers. You should be able to readily manage that, having looked at those two programs. Now we're going to turn our attention to some of the nitty-gritty details of how to write a correct C program. And we're going to look at a very simple program. I'm going to show it in its execution window, but first I want to discuss what we're going to look at. So this program is going to print a sum of two floating point numbers, and it's going to use simple I/O. It's going to use a scanf to read in the values and then printf to show the results. Now, the elements of a C program are made up of characters, so it's just like an essay in English, except an essay in English could be understood even if you have misspellings and punctuation errors. In case of a C program, spellings, punctuation errors, mistakes of that kind get caught by the compiler, and the compiler won't let you run the program, even though you think you understood and it should have understood these simple mistakes. Now, hopefully, a good C compiler will give you informed messages that make it clear what it thinks is wrong. So, first off, a program in C assembles a bunch of characters into what we call tokens. And let's look at a little of what a token is. So, these tokens or lexical elements might be comments, for example. A comment is something that starts with /*, and then can be any set of characters. So those set of characters get ignored until you see an asterisk slash. What if you forget the second part or write this incorrectly? Then this is going to go on forever, and you'll get some error message, hopefully, that'll say you didn't complete your comment. A second thing you'd see in that we've seen already in C programs are preprocessor directives. And the biggie is sharp include. So a preprocessor directive starts by putting a sharp. Typically, by convention, the sharp should be at the beginning of the line. And then we have a number of possible special words. And include is one that says to the compiler, the following library should be included. And we, of course, have already made use of standard I/O. But there are other important libraries like the math library, like the character processing library, like the library that includes timing operations, time.h. And there are multiple very important standard libraries that you're going to have to get familiar with. Another big part of having a program be correct are things like identifiers. And these are possibly multi-letter, but they can be as much as single-letter tokens. So A and B can be an identifier, and we'll see that in the next program. And main is a typical identifier because it indicates it's special in the sense that it indicates where the program is going to start executing. We also have tokens that are operators. So plus is a token for binary operator, or in context, it could be a unary plus. Ampersand is an operator, meaning address of, but again, you gotta have context. So sometimes you could see two ands, and two ands are the operator for logical and. And then there's punctuation, also highly important. So we've already seen punctuators like the open brace and the closed brace and the semicolon. And each has an important use in the language, and you must get them to correct, or else you'll make fundamental syntax errors. So a program must end up being syntactically correct. So we write a program, we get our ideas down, and then we have the compiler check that it's syntactically correct. So here's a possible syntax error message. We'll have int main paren, and then rather than a curly bracket, we might mistype and have an open parenthesis, and that would be wrong. So the compiler will issue some message. Hopefully it'll be informed. It almost always points you at where it sees the beginning of the error, and then hopefully it gives you an English language message that is helpful. But you have to make sure you understand where the error occurs and how to correct it. Then harder than that is to get the program to work right, semantically correct. It works. And here is where we possibly repeatedly run, modify, and retest the program until we get it right. Okay, the next segment will go on to the actual code for the program in which we've seen these tokens parsed by the compiler compiling, and then executing. Okay. This topic will be a very simple one. But a super important one. You just have to work as long as I had at programming to understand how valuable it is to properly comment your program. So what is a comment in the C programming language? We're in my terminal environment on my Macintosh, a Unix environment. And let's look at a particular program that we've already may have seen. Let's look at circle.c. So and here we have our comment, and we're used to now writing code in which We start with a backslash star and a star, an end and a star backslash, and then we can write whatever we want in here. All of this gets discarded. So if you recall how the C compiler works, first off, there's a preprocessor. The preprocessor puts in whatever code is necessary. There's what's called a tokenizer, and the tokenizer goes and looks through things and discards this. So this, in effect, becomes empty space. So why is it so important? It's important for documentation and readability. In order to be able to maintain or modify the program and understand its use, we want the program to be literate. So we could, let's say, add some more comments if we want. Let me add some other comments here. Area in kilometers. So there's a comment. Now I'm going to show you a different comment style. In original C and ANSI C for a long time, the only kind of comment was backslash star, whatever you want, star backslash, and this could be multi-line. But it turns out that's inconvenient, and sometimes it makes for mistakes if you misspell this. But let's put in a rest of line comment. Notice in this case we use 2 backslashes, but we don't have to do anything further, and only the rest of this line is considered a comment. Most compilers, unless you're using something that's probably pre-1988, will allow for this rest of line comment. Let's see if my compiler will allow it. We're going to call in the compile command. No problem. Now, if we want, we can execute. Enter a radius, 2, and that would be the area. 2 meters, we get an area of 12.566 square meters. So comments are critical. We can do them with the classic multi-line comment, or we can use the rest of line comment, the more modern comment. That tends to be less error prone and, of course, fewer characters to write. So in this segment, we're going to look at tokens of the language that are called keywords. Also, in other programming languages, they were sometimes referred to as reserved words. And I'm going to use my browser to look at. You can get many tables for this, but it makes it a little easier. So this is the standard ANSI C recognizes the following keywords. And there are some additional ones, but I'm going to start by grouping them. And it means that they can't be used for other purposes. So you can't use them as ordinary identifiers. Now keep in mind, certain things that look like keywords aren't keywords. So typically on an exam, a simple mistake is to think that main, M-A-I-N, is a keyword because you're seeing it all the time as an identifier that by default introduces the execution of the main C program. but main is just a keyword. Another thing that might be thought of as a keyword is actually a special word for the preprocessor, which is something like include. And words that get introduced by the sharp sign, like sharp include or sharp define, while they have special purpose in the language, in the C compiler system, they are not these reserved words or keywords. Now, a number of the keywords, like double, float, int, long, char, those get used to declare data types. Those are used for the built-in, or what we call the native data types of this language. Another one of those is enum. So they're one category. So let's look at char. We'll get a further definition by clicking on it. Int and char, basic data types for integer and character. Variables of type int are one machine word in length, and that's typically on most machines 4 bytes now. They can also be modified by signed, unsigned, short, and long, but that's for a later time. So character types are very important. They are the basic types that you're going to work with in the language. The int type, which is one of our most basic here, is a range of int typically represented between roughly 2 billion, minus 2 billion, and plus 2 billion. In the signed type and in the unsigned type, it's 0 to 4,294,967,295. Break, continue, go to, for, if. These are all keywords, else, that affect the flow of control of the language. Later, we're going to go and show you what an if-else statement is. We're going to avoid goto, so consider goto obsolete. Goto is a way of jumping anywhere in the program code, and that's considered a no-no. And in fact, some languages now no longer allow goto. Return, we've seen in a lot of our simple programs, and that just means finish the execution of the current function, and if it's return of an expression, it returns the expression value to that function from where it was called. Later, we're going to see fancy things like typedef. They're a way of giving new names to types, or frequently compound types. There's some specialized types like union and struct. Struct will be heavily used, but in part B of this course. And union, not so much. Generally, union can be avoided. Now, among these keywords, auto is obsolete again. Auto is just rarely used, unneeded. It's what's called a storage classification. Among the storage classifications, you have auto and you have register. Again, register is unneeded. Register says, place whatever this is into a high-speed storage. Well, it turns out the compiler can do a better job than you can do. And indeed, modern C systems are running on things that don't need this kind of programmer-directed optimization. So you're not going to see auto, you're not going to see register, you are going to see static, but it has a very special set of uses. Those are storage classifiers. So get used to this keyword list. I think there's about 30 in this keyword list. Most of them are critical concepts, but the nice thing about a language like C, it has a relatively small number of these. In current C++, the number of keywords exceeds, I believe, I'm not exactly sure. Why don't we look it up? So I'm going to use my compiler, ANSI C++ keyword table. And you can see this is a very much bigger set, includes as a subset things that we saw in the other case. And indeed, C will let you migrate to C++, but we're not starting with C++ because look at this table. It's what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's about 96 if I'm counting right, and indeed there are some other things that are special context. So roughly speaking, C++, modern C++ has 3 times the keywords, and you can imagine that in many ways it's 3 times more complicated, though of course you don't have to use the full language. Okay, enough said about keywords. In this lecture, I'm going to talk more about identifiers. When you write code, you will see in the code tokens that we call identifiers. So we've already written code where we see int main paren. The int is not an identifier, it's a keyword. Main is an identifier. It's the name of the function in which execution starts, and the parentheses are not part of the identifier. Parentheses get used for a function call. Now, one of the key parts in writing good documentation in any programming language is proper choice of an identifier, and we have to know the rules for how to choose an identifier. And here's a shorthand for the rules. I'm not going to do much of this, but I'm going to explain it. This is what is called a syntax equation. Identifier is sitting on the left side. An identifier in C is made up of a letter or underscore character in which you have at least one. Letter or underscore. This straight line means or, letter or underscore. And when I subscript by 1, it means I have to have at least one of these. And then following it, I have a letter or underscore or digit, and I can have that 0 or more times. The plus sign means as many times as I want. So identifiers can be arbitrarily long. Generally speaking, you're not going to see identifiers that are more than 10 or 12 characters. That would be as big an identifier as you're likely to see. In C, what conforms to this? Well, the simple one-letter identifier K, frequently used for integers that are auxiliary integers in writing your code. Underbar printf, that could be an identifier, and in fact, that's probably the identifier that the systems programmers used when they designed the printf function. Here is a common thing you see. 2 words. When you have the 2 words, you have two underbar words. The underbar, or the underscore character, I should say, the underscore character is used to separate distinct words. So when you want an identifier, but in English you want to have more than one word in your description, one convention is to use underscore. Another convention is to tie the two words together with a capital. So to capitalize W, the beginning of the second word, and that would also be another standard convention. What you shouldn't be doing is mixing them. And then here's another standard identifier, my underscore DNA 23. And remember, once we're past the first digit, we can use digits as well. What won't work as an identifier? The sharp character. So sharp me is not an identifier. Sharp is not allowed anywhere. So or me sharp would not be an identifier. Here, rather than underscore, I'm using minus, and that would be the expression unary minus x. X could be an identifier, but minus x is an expression. And 23 my DNA is not an identifier because the first character of that sequence is a digit. So that's not allowed. So digits are allowed anywhere but in the first character. Underscores and alphabet are allowed anywhere, including the first characters. Now, good choice of identifiers in your program help you document the program and make the program readable. Main, printf, square root, sqrt, those are actually things you'll see very commonly. Printf and square root come from standard library. And Superman, if somehow you're writing some code to exhibit something to do with the character Superman, maybe you'd call that, you'd use that as an identifier. That gives you a clear image, as does radius. And I as well. You have, it's a convention in the community, in both the programming community and mathematics community. When you want something that's for counting, you can use I, J, and K. Also, you frequently can use N as another understood integer. Those would all be good choices. Of course, you have to use them for the right purpose. Here are some things that might be bad choices. grx33 underbar pp underbar 25, I underbar am underbar 4 words. Well, grx33 and this underbar pp stuff, we have no concept of what they might be. So they're not going to be readable. They're not going to provide some kind of documentation. I am 4 words makes sense, but we've mixed two conventions. So that sort of would, in a way, take away from the goodness of I am 4 words. Other things we aren't going to necessarily know if they're good or bad. Let me put some up. They're going to have the right context. So data may or may not be good. It may not be adequately descriptive. Maybe you need height data or weight data or something else. Mixapitalik. I'm not sure I'm pronouncing that right. Maybe that's an okay identifier. Maybe not. Let me exit this. If we look in our browser and we look up DC cartoons, Here's Mr. Mxyzptlk. He's a typical foe of Superman. Superman always has to get him to say his name backwards, which again is very hard to pronounce. I'm not sure if it's Kitazimavik, whatever. And again, if you were writing some movie with Superman and Mxyzptlk, it might be an appropriate identifier. X might be an appropriate identifier, especially if it's something like a coordinate in the XY plane. Then it would make perfect sense. Again, we've said if we use J for integers, fine. Q may be good or bad. Maybe it's obscure. Maybe we're doing something like logic programming. And in the logic community, P and Q are typically chosen to mean Boolean variables. So if we were doing logical evaluation, P and Q might be quite appropriate. Again, that's contextual. So they might be either good or bad. Let me finish by looking at a very simple program that hopefully follows these constructs. Here's a piece of code. It's for computing the area of a circle. Notice we have main, that's an identifier. The capitalized pi would be an identifier in C, but that's a preprocessor command, and in the syntax, this must be an identifier, and then it's associated with this constant value, and it's typical. Another convention is when you have such a constant, you capitalize it. Again, there are community conventions that should be understood to make your program readable. You want an experienced C programmer to say, aha, I can read that and understand it clearly. So here we have two identifiers, area and radius, and we understand their meaning. That's how we're going to use them in the program. Double, of course, is a keyword. Then we have printf, scanf. They're both standard identifiers found in the IO library and standard.io.h. There's area equals pi times radius squared, and so on. So this program abides by my conventions, has good choice of identifiers. We've already talked about operators and operator precedence, which is very important to figure out how expressions will be evaluated. And there's quite a few levels of operator precedence. We've already seen 4 or 5 of these. I want to go into a little more detail on this. And so I'm going to put up the complete operator precedence table for the C language. And we see it here. Found it on the web. It's a nice version. There are many. This is copyright William Swanson. And notice what he says about the table. Operator precedence describes the order in which C reads expressions. For example, expression A, 4 plus B times 2, contains 2 arithmetic operators. Actually, technically, there's the assignment operator as well. An addition and a multiplication, so there's actually 3 with assignment. Which comes first? Well, the 4 plus B does not get evaluated first. That would be a left to right order, which isn't the case. Times has the highest precedence. So first, whatever B's value would be multiplied by 2, and then 4 would be added to the result. Now, there's also a notion of associativity, whether things associate left to right, which is but some operators do and others go right to left. So let's look at the different levels. There are something called primary expression operators. Those include postscript plus plus, postscript minus minus, the auto increment and auto decrement operators. It also includes something we will use later, which is indexing, and also includes function call, which we've already seen when we call main. Then there are a bunch of unary operators. They have the next highest precedence, and among them is star, which in this case means dereferencing, and we won't see that until much later in this course or the next course. Also, address of, which we've seen with scanf, the unary plus and the unary minus. So you see plus and minus here, and those are binary. So unary minus and unary plus bind more tightly, have higher precedence than the binary operators. So you could say plus B plus A. And the plus B, while in effect it's a no-op, is first do this unary plus operation, which doesn't have much value. Then there's a logical negation, very important, especially in logical and relational expressions. Then there's the prefix auto-increments and auto-decrements, and we'll see later that we need typecasting, and we also will have a special operation called size of, which gets us the size of some expression, how it's stored, how many bytes. Here we have operators we've already used a fair amount. We've had times, divide. Divide is actually two operators. It could be integer divide or floating point divide, and modulo. Here are the binary plus and minus, and then below it are some bit shift operators, and then relation operators, less than, greater than, equal, less than, equal. And then equality and inequality. The logical is A equal to B or is A not equal to B. Then the bitwise operator, ampersand, which is different than the use up here. So one thing that's confusing about C is the overuse of symbols. So you have to understand a symbol in the context. So this is a bitwise and. This is an address of and we'll see later, ampersand is a logical and, just as these two side arrows are logical or, whereas this is a bit shift, and this is also a bitwise operation. We won't get to use a lot of these operations, especially the bitwise operations. They're rather advanced. You should know about them. This is a fancy ternary operator. It's ternary because it has three arguments. We'll get to see it shortly, but again, it's a bit esoteric. Finally, we have these assignment operators, the normal one, just assign, then plus assignment, minus assignment, times assignment, etc. And finally, we have the lowest precedence operator, which is a comma operator, which is associating left to right. And the comma operator is quite interesting, though again, it shouldn't be used too often because it's fairly subtle. And it means first evaluate in a left to right order the first expression, and then go to the next expression, and then go to the next expression. So also, the comma operator forces a sequence of evaluation, which is sometimes useful. To make sure you understand how these things work, at least in things you've already used up to now, you should be able to do, what's 3 times 5? All right, that's pretty easy, I'll tell you. It's 15. Now, what's 3 times 5 plus 2? Here you have to know that the plus 2 is added on later, right? Times goes first. Now, you can override precedence with parenthesization. So 3 times 5 plus 2 is different than 3 times 5 plus 2. However, you could also have had paren 3 times paren 5 plus 2. And that would have just reinforced the implicit ordering already. So again, you can work through a bunch of these. Just make sure you understand how they work, how to do the order of evaluation. Here's that funky 8. Is it equal to plus 8? Remember, this plus is a unary plus. And then here we get into the difference between integer divide, 3 integer divide 5 versus 3.0, which is a literal double, a constant that's taken from the doubles, divide 5. And you should understand why these give different results. Okay. We'll also do a quiz on this. In this segment, we're going to talk about expression evaluation. C is a language rich with operators, and it's very important to know how the operators allow combination, in what order they're applied. I'm going to show you some very simple cases so you can get the central idea, and the central idea is going to be know how the operator works, know its precedence, and know its associativity. So we're going to start with 3 very simple variables. As we declare them in C, we would say int A is initialized to 1, equals in an declaration is the initializer symbol. Int B is initialized to 2, and int C is left uninitialized. Normally, most systems would make that 0. So we have 3 variables to work with in our code. Here's a very simple expression using those. C is this equals means assigned. So in this case, we are seeing an assignment statement. Read that as C is assigned the expression A plus B, semicolon is a end of the operation. So it's signaling a sequence, what's called a sequence point in the computation. Everything that happens on that line, and then you're finished, and then you go on to the next line. Now, as we know, A was initialized to 1, B was initialized to 2, so we would expect C to become 3. So this is a assignment expression. Inside it is a binary plus operator, and that says C is assigned a value of, and here we use parentheses, A plus B. And parentheses are critical in the C language when you're evaluating expressions, because they always override any other part of the expression's precedence. So they clearly show, if you're confused otherwise, or it's a very complicated expression, that this is how you want the order of evaluation to occur. So as we just said, C becomes 3. That should be straightforward. Let's go on. precedence? Well, we have something like 16 levels of precedence in C operators. Things that are very low precedence, for example, tend to happen later or last. So assignment itself as an operator has very low precedence. However, certain operations, like unary operations, like the operation negation, which is found when you're doing some logical expressions and where you use the exclamation point, is a very high precedence operator, as is something like auto-increment or auto-decrement, which are operators that use the symbol plus plus and minus minus. And then somewhere in the middle are arithmetic operators. And in the arithmetic operators, you have multiply, for example, which in this case is featured with this star. And that has a higher precedence than simpler arithmetic operations, plus and binary minus. By the way, note that you can also have unary minus and unary plus. And the only reason you would know the difference is context or parenthesization. And a unary operator like these are higher than the corresponding binary plus and minus. So binary plus and minus take two arguments, unary takes one argument. And then times, and indeed things like multiply and divide are higher precedence again. And there's also on that level the remainder operator percent, which again, or sometimes called the modulo operator or remainder operator, which is also a higher precedence, equivalent to a multiply or a divide than the addition operator or subtraction operator. Why is that important? Because if these get mixed up in an expression, you have to know which goes first. The other thing you need to know about is associativity. How do the operators associate? So when you have an operator A plus B plus C, this has got two operators, which goes first? Do you apply B plus C first and then do A? Or do you do A plus B first and then C? And it turns out that these operators occur left to right. And the overwhelming number of operators are left to right. And we show the equivalent parenthesization here. So we would get A plus B, parentheses, plus C, parentheses, if we wanted to fully parenthesize this expression to make it clear what the implicit order of evaluation based on associativity were. Now, looking at this other expression, A assigned B assigned C assigned 3, we get right to left. That means the C assigned 3 occurs first, then the B is assigned that expression value, then the A is assigned. And what you'd all end up with is everything would end up being 3. All right? Try to absorb that. Make sure you can write code of this kind and know how to evaluate it. And we're going to go on to more complex expressions with different operators involved. Okay, we're going to go on to more complicated expression evaluation. We're going to look at some more involved cases. One of the things that gives a lot of people trouble at first is to remember that tokens like the slash token have different meanings in different contexts. So besides the fact that a slash token can be used to be part of a comment, a single slash is generally a divide in an expression, but that divide could be either the integer divide operator or the floating point divide operator, and that gets determined contextually. Similarly, people have trouble with the remainder or modulo operator, the modulus operator. Somehow they don't use that as much in daily practice, so it's hard for them to remember how that works. Then there are operators that are unique to the C language, and they include auto-increment and auto-decrement, and they are plus plus and minus minus. And then there are operators that are based on assignment, so they are ordinary assignment, but also an operator like plus assign. So you might see plus equals or minus equals. But when you see equals equals, that itself is a logical operator. So context means a lot. And I shouldn't say these things are unique, because while C pioneered much of this stuff, they do get used in typically languages derived from C or with some inspiration for C, so you'll see such operators in Java and C++ as well. Now, if stuff gets too confusing in expressions, then to unconfuse yourself and people reading the code and maintaining the code, use parentheses. And keep in mind that parentheses override the built-in precedence and associativity of the operators. So A times B, which is high precedence, then plus, if you had A times B plus C without parentheses, it would mean that first thing. It would mean first do A times B because of its higher precedence, then add in C. But if you wanted A times B parenthesize C, then you'd have to use parenthesize, because that would override the precedence and associativity of those, the built-in ones for those operators. There are also gotchas that you have to keep in mind, and a typical one is the use of divide when it's an integer divide. You don't have this problem with multiply, but 3 divides 7 is going to be 0, whereas 7 divides 3 is going to be 2. And in those cases, there would be a remainder, and the remainder just gets thrown away. But 5 divide 2.0, because 2.0 is a floating point constant, is indeed 2.5, which itself is a floating expression. Finally, the modulo operator, as I say, you have to familiarize yourself with it if you haven't used the idea of modulus for a while. That's just what a remainder is in an integer divide. So 3 modulo 7, a remainder would be 3, or 7 modulo 3, the remainder would be 1. Here's the use of pre and post increment. These are specialized but very useful because they abbreviate what would take some more writing. So the pre-increment, namely plus plus b, what it means is b is assigned b plus 1. So b plus 1, the increment, gets done first. Then the assignment a is assigned the resulting value of b after the increment. In the post case, which has higher precedence, by the way, a assigned b plus plus, it's the equivalent as a is first assigned b. So if b was 5, a would be 5, but then b would become 6. All right, so I hope you'll experiment, and I'm going to show you an experiment right now. I'm going to switch over to my runtime window. So here's some code I wrote earlier to experiment, and this is code that you should try to either copy or write your own code of this kind and just try to check your understanding of evaluation, make sure what gets done on the machine is what you expected. So in the first case, we have equals sign meaning initialized. So A is initialized to 5, D is initialized to 0. Then we have an expression where C is assigned A minus B. Well, A is 5 and B is 7, so we'd expect 5 minus 7 to be minus 2. So if we use that print statement, we should see A is equal to 5, B is equal to 7, C is equal to minus 2, and D is equal to 0. Now, in this part of the code, we're seeing how integer divide would happen. So 5 integer divides 7, that's going to be 0. D will be equal to 7 divide 5, so that will be 1. If this had been all in floating point environment, if everything had been set up as floating point, then instead you'd have the equivalent of 5/7 in floating point, or 7/5 or 1.4 for D. But that won't happen. You're going to get 0 and 1. Also, further on here, I won't look at the module, I'll let you work that out, but here's an interesting one. Here we see the difference between unary minus and binary minus. And unary minus has higher precedence, so that occurs first. So 5 becomes minus 5, and then we have a binary minus where we subtract 7, positive value 7, and the result should be minus 12. Here we're seeing the difference between prefix, auto increment. So A will move from 5 to 6, but this is postfix auto increment, so B remains 7. So 7 plus 6, C will become 13. But then when the whole thing is executed after assignment, then B will become 8. And here we see the plus assignment operator. So this means whatever D's value was, where in the earlier case D would be minus 12, we would add in 5, so we'd end up with a minus 7. So again, try to understand all this, and then here's the actual running of the program results in these values. And I will write a quiz for you and most likely put something of this kind on the class final.
So finally, we'll talk about some built-in limitations to the Bitcoin protocol and why it's challenging to actually improve them. There are a lot of hard-coded constants that are implemented into the Bitcoin protocol, which were chosen when Bitcoin was proposed in 2009, before we really had any idea that it might grow into this globally important currency. So the most important limits are probably the limits on the average time per block, the size of blocks, the number of signature operations in a block, and the divisibility of the currency. The limitations on the total number of Bitcoins in existence, as well as the structure of the mining rewards, are very likely to never be changed because the economic implications of changing them are too great. Miners have invested a lot of real-world resources into becoming miners, assuming that Bitcoin rewards would take a certain shape and that the limited supply of Bitcoins would remain the way it's been planned. So if you change that, that would have large financial implications for people. So for that reason, the community has basically agreed that those values, whether or not they were wisely chosen, we're basically stuck with. Some other changes you'd like to make seem like they would make everybody better off. Things about Bitcoin that just weren't quite properly designed at the beginning, but are also hard to change. The main aspect of Bitcoin that people are worried about and would probably like to change if they had time to design it over again are limits that affect the throughput of the system. How many transactions can the Bitcoin network process per second? So this limitation comes from the hard-coded limit on the size of blocks. Each block is limited to 1,000,000 bytes. And each transaction has to be at least 250 bytes. So if you divide through and the fact that blocks are found every 10 minutes, you're left with about 7 transactions per second, which is all that the Bitcoin network can handle. And it seems like tweaking those numbers would be very easy. It's just one constant in a file somewhere that you'd have to change. It would actually be very hard to change this in practice for reasons that will become clear in a few seconds. So how does 7 transactions per second compare? Well, if you went down to the offices of Visa and told them I'm proposing a new payment system that can handle 7 transactions per second, they would probably tell you, that's terrible, and then they would laugh and throw you out the door. They've been working for a long time to build a payment network that goes way bigger than this. So it's said that Visa handles on average about 2,000 transactions per second around the world. And on the busiest times, so think the Saturday before Christmas when everybody's out shopping and swiping a credit card, the Visa network can handle about 10,000 transactions per second. And other payment card networks are similarly big. You can also look at PayPal, which is not as big or as old as Visa, but even PayPal can handle 100 transactions per second at peak times, so an order of magnitude more than Bitcoin. Another limitation that people are worried about in the long term is that the cryptography in Bitcoin is fixed. There's only a couple of hash algorithms, and there's only one signature algorithm, which is elliptic curve DSA, over a specific elliptic curve called SEC-P256. And there's some concern that over the lifetime of Bitcoin, which people would like to be for a long time, this algorithm might be broken. Cryptographers might come up with a clever new attack that we haven't foreseen, which makes this an insecure algorithm. And the same is true of the hash functions. Hash functions in the last decade have actually seen steady progress in cryptanalysis, with SHA-1, which is included in Bitcoin, already having some known cryptographic weaknesses. So to change this, we would have to extend the Bitcoin scripting language to support new cryptographic algorithms. So what would it look like to make a change like this, where we just said, we had a problem in Bitcoin, we're going to release a new version of the software, and everybody is going to have to switch? This is what we would call a hard forking change. So in practice, it's impossible to assume that every node would upgrade. Some nodes in the network would fail to get the new software or fail to get it in time. And what would be the implications of that? Well, let's take a look at a network here where most of the nodes have upgraded, but there are a few that haven't. And now let's say one of the new nodes says, hey, I found this nifty, great new block. Maybe it has some new signature algorithm in one of the transactions using the new features that we've added to Bitcoin. So block 4 has found this and says, OK, I'm going to update and say that's now the newest block. So I'm at block index 24. The rest of the network is at 23. But I'm going to propagate that to all of my peers using the normal block flooding algorithm. So node 4 is going to send block 24 out to its neighbors, nodes 3 and 2. Node 3 is going to get it and say, great, I got that one. I'll update my version of the blockchain to have that as the newest block. Whereas node 2 is going to say, that's crazy. You have some operation code that's disabled or reserved. I have to reject this block. I don't understand it. I can't accept it. And similarly, when it gets over to node 6 is also going to say, nope, I can't accept that block either. And now you're going to end up in a state where the new nodes have one picture of the blockchain, and the old nodes have all refused to accept this latest block. So the new nodes will go off and work on a version of the blockchain, including this new block with the new fancy feature. And the old nodes will all be stuck on an old version of the blockchain. And unfortunately, they're never going to catch up, because until they upgrade their software, they'll keep rejecting all of the blocks that are proposed by the nodes in the network that have upgraded to the new version of the protocol. So the reason it's called a hard fork is that the blockchain will split. Every node in the network will be on one side of it based on which version of the protocol it's running, and they'll never join together again. And this is considered unacceptable by the community, that old nodes would effectively be cut out of the Bitcoin network if they don't upgrade their software. So by contrast, there's an approach called soft forking, which tries to avoid creating a permanent fork like this. The observation is that we can add new features to the Bitcoin protocol if they only restrict the set of valid transactions or the set of valid blocks. Because we want to avoid this hard fork situation, we can try to add new features in a way that will cause only a soft fork. So the key to making this happen is that the new features can only make validation rules stricter. They can only limit the set of blocks or the set of transactions that are considered valid. So the new nodes in the network will be enforcing some new, tighter set of rules. So we're relying on enough nodes switching to the new version of the protocol that they'll be able to enforce the new rules, knowing that the old nodes won't be able to enforce the new rules because they haven't heard of them yet. There is a risk here, which is that old nodes might be mining an invalid block because they include some transaction which used to be valid, but according to the new, more strict rules, is not valid anymore. So that could be bad. Those nodes could waste a lot of time mining a block that the new nodes will reject. But when they try to announce that new block, the new nodes will reject it. The old nodes will at least figure out that for some reason, even though I don't understand the reason, the rest of the network has rejected my new block. Therefore, I should move on to the version of the blockchain that all of my peers have, and it won't be a hard fork. They'll have a temporary fork by virtue of the new block they tried to mine that was rejected by the network, but they'll recover and get back onto the main chain. So the classic example of a change that was made via a soft fork was pay-to-script hash, which we introduced earlier in the section discussing the scripting language. So the view of pay-to-script hash from old nodes, and again, pay-to-script hash was not present in the first version of the Bitcoin protocol, they see this script as really simple. All it's doing is hashing this one data value and checking to see if it's equal to the value specified in the output script. The old nodes never do that second step of verification in pay-to-script hash, where they then check to see that that value before being hashed runs as a valid script. So what could we possibly add with a soft fork? Pay-to-script hash was successful. It's also possible that new cryptographic schemes could be added by a soft fork, or that we could add some extra metadata in blocks that had some meaning. And the place you'd add this is in the Coinbase parameter. So today, any value is accepted in the Coinbase parameter, but we could in the future say that the Coinbase has to have some specific example. One idea that's been proposed is that in each new block, Coinbase contains a Merkle root of the entire set of unspent transactions. It would only result in a soft fork because old nodes might mine a block that didn't have the required new Coinbase parameter that got rejected by the network, but they would catch up and join the main chain that the network is mining. Other changes might require a hard fork. That would be if we wanted to add new opcodes to Bitcoin, change the limits on block or transaction size, or do a lot of bug fixes. So for example, the bug I showed earlier, where the multisig instruction pops an extra value off the stack, that would actually require a hard fork. And that's the reason why, even though it's an annoying bug that people wish wasn't there anymore, it's much easier to just leave the bug in the protocol and have people work around it, rather than have a hard fork change to Bitcoin. So all of these hard forking changes, even though they would be nice, are very unlikely to happen, at least within the current climate of Bitcoin. But a lot of these ideas have been tested out and proved to be successful in alternative currencies, which start over from scratch, and we'll be talking about those in a lot more detail in our lecture on altcoins. So I spent a lot of time talking about details today. I know this has been a long lecture with a lot of technical detail, very hard to absorb it all at once. So like I said, I would certainly recommend you can go online, and see some of this stuff in practice, see what blocks and transactions look like, it took me a couple of times looking at them before I really had a good sense of what was going on, but I think the practical examples do really help. In the next lecture, given all these mechanics we've introduced, we're going to look at the human side of things. Because after all, human beings aren't Bitcoin nodes, and you're never going to run a Bitcoin node in your head. So how do you as a human actually interact with this network to get it to be usable as a currency? How do you find a node to tell about your transaction? How do you get Bitcoins in exchange for cash? How do you store your Bitcoins? So all of these questions are crucial for making a currency that will actually work for people, as opposed to just software.
In this segment, we'll talk about the structure of the program that includes declarations and an especially important operator, assignment, and how it relates to expressions as well. And all this is wrapped up with types. So we're going to talk in detail in the next few segments about the type logic of the C programming language. Now, types. Some of the types we've seen already are int and double. There will be other types. There will be other simple types like char, float, unsigned, and then there'll be more complicated types later on that involve structs. For the moment, we'll concentrate on these two distinct types. Int, which is in effect an integer type, supposed to represent precisely the whole numbers, and double, which is a floating point type, which is supposed to represent scientific numbers with a very large range. Now, a simple declaration is going to look like a type followed by an identifier with a semicolon. So here we see a simple example on this side. Then a more complex example is a type identifier followed by the equals sign, the equal character, and an initializer. This is not assignment, this is initialization. It occurs in the declarations. Declarations, by the way, occur at the head of a body of code or at the head of the program. And here we have, again, a very simple example. Int, the variable a assigned to. So there we mean that we're going to, in that piece of code, treat a as something that can get different values as long as they're integer, as long as they fit within the type int, and we'll explain more about what it means to fit in the type int, and 2. Finally, we can have a more complicated type declaration in which we have a list. So here's one of those. Int a assigned or initialized 3, comma. So it's a comma separated list. It can be arbitrarily long, and this has 2 variables, one initialized to 3 and one initialized to 5. Okay, let's restart. Here we have a piece of code that I already typed in. It's supposed to show you an example of the use of elementary declarations and assignments. In this piece of code, again, at the head of what's called the block starts with at open brace. We have a declaration list with initializers. So A is of the type int, B is of the type int, C is of the type int, And if we think about what's stored in their memory location, A is 5, B is 7, C is 6. And then we're going to do a simple averaging, and we're going to use a variable average, and that average is going to be initialized to 0.0, though that may be unnecessary, because it's just good practice to initialize variables, because sometimes when you forget to do that, it can lead to errors if you allow the system to do the initialization for you. Here's a printf that'll show us that we assigned what we've assigned, and then we're going to do an average. And in this average we see A plus B plus C. Normally that's an integer expression. We divide by 3.0. Why? Because if we divide by 3, this will be purely an integer division, and we may have a rounding error. But we want it to be done in double. We're going to talk more about why this occurs as a double. This expression will occur as a double. So this is overall an assignment expression, but conversion would have been, if there was a 3, we would make this an integer expression and then assign it to a double. In this case, this is a double expression assigned to a double, so there's no conversion. Again, as I say, difficult topic, very tricky. We'll talk a lot more about conversion. And here we just print it. So it's a very naive program. Let me escape. And I compiled it already, and let me run it. And sure enough, A is 5, B is 7, C is 6, and the average is indeed the floating point number 6.0.
Welcome to Lecture 4, where we'll talk about how we store and use Bitcoins in practice. In section 4.1, we'll talk about the simplest way of storing Bitcoins, and that is simply putting them on a local device. Now, just to review, in order to spend a Bitcoin, you need to know two kinds of things. First of all, you need to know some information that's stored on the public blockchain. You need to know what the identity of the coin is and how much it's worth, for example. And along with that, you also need to know the secret key of the owner of the Bitcoin. Presumably that's you. Now, if you think about it, the first piece of information, being on the public blockchain, you don't need to worry too much about how to store it because you can always get it back when you need it. But the secret signing key is the thing that you'd better keep track of. So in practice, when we talk about how you store your Bitcoins, what we're really talking about is how you store and manage your keys. And that's going to be the main topic when we talk about how to store Bitcoins. So really, this lecture, which we titled How to Store and Use Bitcoins, might as well be called How to Store and Use Secret Keys, because that's really what it's about. Okay, now, when figuring out how we're going to store and manage our keys, there are three goals that we have in mind. The first goal is availability. You want to be sure that you can actually spend your coins when you want to. The second goal is security, and that is that nobody else can spend your coins. If someone gets the power to spend your coins, they could just send your coins to themselves, and then you don't have the coins anymore. And the third goal is convenience, just that whatever you do, it's relatively easy to use. Okay, so the simplest approach to managing your keys, what to do with them, is just to take the key and store it in a file and put that file on your own local device, on your computer, on your phone, or on some other kind of gadget that you carry or own or control. And evaluating that method against our three goals, well, for convenience, it's great. Nothing could be better than to have, say, an app on your phone where you can push a button or swipe something and spend your Bitcoins. So for convenience, it wins. But when it comes to availability and security, storing things on a local device in a simple way is not such a great idea. And the reason is, first, when you get to availability, that your key, your coins, are no more available than your device. That means if you lose the device, if the device crashes and you have to wipe the disk, if your file gets corrupted or something like that, you're out of luck. The key is lost, therefore your coins are lost. Similarly for security, your keys, therefore your coins, are just as secure as your device. If somebody managed to break into your device to compromise it, if they can put malware on your device, a virus or something like that, then they can get the key, leak the key to themselves, and they can then send all of your coins to themselves. So although storing things locally is very convenient and very simple, it really isn't up to the task for availability and security. And the way to think about this is a lot like carrying around money in your wallet or your purse or in your pocket. It's useful to have some spending money, but you don't want to carry around your life savings because you worry that you might lose it or that somebody might steal it. And so what you typically do is store a little bit of information, a little bit of money in your wallet, and keep most of your money somewhere else. Now, in order to do all of this, we typically, if we're going to follow the local storage approach, we typically use wallet software. And that's just software that manages all the details of keys and makes things convenient. It keeps track of your coins. It gives you a nice user interface. If you want to send $4.25 worth of Bitcoins to your local Starbucks, the wallet software will give you some easy way to do that. And by the way, if you're using wallet software, once you're using software to manage keys and such, it's a nice trick, it's a useful trick to use a whole bunch of different addresses, a whole bunch of different keys. So rather than taking all of your coins and paying them to one address and controlling them with one key, you can have a separate address, a separate Bitcoin address, and a separate key for each coin. That keeps things separated so that you get a maximum degree of anonymity or privacy. And you don't need, as an individual, to worry about the management of all these different keys and addresses. Your wallet software takes care of it for you and just gives you a very simple interface that says how much is in the wallet and lets you spend it. The wallet software figures out all the details of which keys need to be used and how to generate new addresses and all of that stuff. So one thing you need to do if you're going to be able to receive Bitcoins in payment into your wallet or spend them to somebody else is you need to have a way of exchanging an address with somebody. So you can give them an address or receive an address so that payments can happen. And there are two main ways that addresses are encoded or conveyed in this way. The first one is as a text string, and the second is as a QR code. So as a text string, what we do is we take the bits of the key and we encode it as a number in base 58 notation, and then we use these 58 characters to encode the digits in our base 58 notation. So what this is basically is it's all of the digits and capital letters and small letters, except that they've taken out a few that might be confusing or might look like each other. For example, capital O and 0 are both taken out because they look too much alike. But other than that, most of the characters are here, and you can encode first in base 58 notation and then using this alphabet. The second method for encoding a Bitcoin address is as a QR code, something like this. This is a simple 2D barcode. And you can do something like point your phone at this, take a picture, and your phone can scan it and recover the bits of the address. And so this is the sort of thing you might use, for example, in a store, or if you want to have a phone-to-phone communication. My phone might display a barcode like this, which is my address on it, and your phone might take a picture of it in order to get the address. So this down here actually is an active address, and if you'd like to give me some Bitcoins, feel free to do so.
So let's continue to talk about the C fundamental types. There will be other types later on, like pointer types and struct types and enum types. But for the moment, we're going to concentrate on a fairly simple set of types. Maybe not that simple. And our early computations will do a lot with int and double and char. And intuitively, you can understand that a char might be a special character like A or a capital N, or the character that's the digit 5, which is going to be different than the value 5, or an unprinted character that moves your screen a line, so that's represented by \n. So the characters can represent what's called the ASCII table of characters. It's typically all the lowercase, all the uppercase, punctuation, operator characters, digits, and some special characters like new line. The integers are pretty much what you're used to since grade school. They're numbers like 0 or -3 or +77. And then finally there are doubles. These are more like the scientific notation. And there you get numbers like 1.245 or 3.2 with an E, which designates that something is an exponent. The exponent is a power of 10, so it's 10 to the 5th. So that's going to be 320,000. Then we're going to allow the fundamental types to have further modifiers. The two critical modifiers are going to be unsigned and long. The idea of unsigned is going to apply to strictly the integers, and that's going to mean that you're going to rule out the negative numbers. Long is going to apply to both the integers and to the doubles, and they're going to mean, well, we might have a range, which typically for the integers is plus or minus 2 billion, and we want a longer range. So that will increase the range of those numbers significantly, and we might need it for a bigger calculation over bigger numbers. Finally, the same thing is true for doubles. We're actually going to have 3 kinds of doubles. We're going to have float, double, and long double. And on a typical implementation, these are going to be longer and longer, and therefore capable of storing a bigger and bigger number. Well, it's not like mathematics. It's not like you can imagine a number like pi in which there's an infinite number of decimal places. So the mathematician's conception of pi is potentially this infinite string. That's not doable. The computer memory is a finite resource. It's organized in terms of bytes. A byte is a unit of memory, which is conventionally 8 bits, and 8 bits can only store so much information. Basically, they can store 2 to the 8th. So here's a number that could be stored. Typically, these things are bits, so 0, 0, 0, 1, 0, 1, 0. Remember, computers are binary, and they store bits. They store them somehow electronically, magnetically, unless you're going to work with some kind of fancy quantum computer. But on all our actual digital computers, a modern digital computer uses a base 2 designation and bits to represent whatever you need to represent when running a piece of computer code. Well, if you look at this, this is the zeros place. This is 2 to the 4th, 2 to the 3rd, 2 to the 2nd, 2 to the 1st. Excuse me. So 2 to the I have this wrong. This is 2 to the 4th, which would be 16, and 2 to the 2 squared is 4. So we're going to actually get the number 20. Very easy to make a mistake if you're not a computer. On a typical machine, an int is 4 bytes, and an int can be used to represent between roughly 2 billion, minus 2 billion, and plus 2 billion. This is more exact. So actually, this is equal to 2 to the 32nd minus 1. And that shows you 4 bytes can be used to store 32 binary digits. One of the digits is going to be used for the sign, so that leaves 31 digits for everything else, and that's why this can be roughly 2 to the 32nd minus 1. Now, when you write your code, you need to know what is representable. The way you can find that out, you can see what a type will So we're going to discuss the fundamental type char. Char is going to let us do a lot of text processing. And char is the constituent in a string. Later we're going to understand how strings are just series of char. Actually, when we learn more about that, we'll see that a string is basically an array of char with a sentinel character at the end, which is basically a 0. So char is a fundamental data type, and a literal or constant char includes things like the lowercase letters. They're represented in your code as single quote x single quote, but also you could have a digit like 7, and it would be represented again, unlike it wouldn't be 7, because if 7 was without the quotes, then it would be the literal or constant int. And then, for example, there are also, and we've already used them, non-printing characters, characters that don't show up directly on the screen but do something. And the most common one is \n, which tells you to advance to a new line. Now, you don't have to memorize this, but in most texts or online, you can find the values of the standard 0 to 127, so it's actually a table of 128 characters that can be printed, or the non-printing characters that will do some action on your computer system. And among those characters are, for example, the uppercase. And what's nice about the uppercase, if you remember, capital A is an integer value 65, then they actually appear in the ASCII table adjacent to each other, and capital B is 66 and capital C is 67, and so on until you reach capital C, which is 90. And similarly with the lowercase, though they're in a different place in the table. So a lowercase a is 97, and then it sequences all the way to lowercase z, which is 122. This is a bit confusing. Digits, when you use them as char, have a value. So the digit 0 as a character is actually integer value 48, and it is also a sequence from 0 to 9. So you have all the decimal digits available for purposes of using them as char or internally in a string, and they range from the integer value 48 to 57. And then there are others, all the other characters you find on the keyboard, and these are punctuation characters and operator characters and special characters like $, and they're all available in the ASCII table, and they all have a particular integer value, except unless you're a memorization freak, you're going to have to look them up. But of course you can quote them, and then they will indeed also have this internal integer value. And one of the things about this is you can store these in a byte. So you can use 8 bits and store any of the ASCII values. Now, non-printing characters are very important as well because they promote actions on your computer system. \n, see, you can't have n because that would be printed as n, but \n sort of escapes it. So the idea is \n is a special non-printing character, and indeed when you put it in a printf, integer value is 10, but what it does is advances to the next line on the screen. \a is also a non-printing character, and if its value is 7, and if you were to use it inside a program, it would, on your system, ring a bell or make a sound. So that's the character set you can use. And now let's show a simple program for how that may be used. So I wrote this program to show how it would be used in a very simple way, and just show how the characters, when printed as a %C, see here, %C is in that format string, that's going to print out as a character. Notice the character is declared, the variable C is a character variable, and we're going to assign it, again, quote, single quote, a single quote. And now we're going to print it in 2 different ways. In the first way, we'll print it as a %D, so it should show up as an integer. In the second print, it should show up as a character. And then we're going to do the following to show you that these values, the ABCs, are going to be sequential. So we have 3 characters to print, and they're going to be C, C+1, and C+2. So those are integer expressions, but they're interpreted as a character. So in effect, the ASCII table gets used to show what gets printed. And here, if you run this on your local system, you should hear something. You should hear 3 distinct noises or bells. And here you have this \A, which I talked about as a non-printing character. Of course, there's a non-printing character here too, and that's in the string, and that's interpreted by printf. So printf knows how to interpret that. And if I had put that over here, if I had made that a character to be printed using the %C, then what I see is nothing but an advance of the screen. So let's run this. I already compiled it. And you see its output. The character C has an ASCII value 97. As I said in the beginning of the lecture, that's the character A. So when I print it as an integer, it printed as 97. I print it as a character, it prints as an A. The 3 consecutive characters that got printed are ABC, just as we expect. The 3 bell rings, nothing got printed, but I heard them locally. I don't know if the microphone picked them up, but there was a bing, bing, bing. That were, in fact, the printing of those 3, quote, non-printing characters. We're discussing further material on data types. Probably the most important data type in the language is int. So int gives us a basic way of manipulating integer data, and that data type includes variations on it, and they will be explained shortly. There is a short form, a long form, and an unsigned form. So let me give you my understanding of how to approach learning a difficult subject like programming. In programming, you have lots and lots of stuff. Much of it is obscure. But if you concentrate on the things that are typical, and int is typical as a data type, then you can get 90% of the value of your study or your work by only looking at 10% of the entire language. So this is one of the places where the 90-10 rule shows up. Really make an effort to understand the data type int, and that will help you with all the other and more complicated data types, such as the floating types. On your typical modern machine, an int is stored in 32 bits. That's 32 zeros and ones. And it's even worthwhile, especially if you're going to go into computer science, to learn how to work in binary. That's the base 2, as opposed to how we're writing most things, which are base 10. It's also worthwhile to learn how to write an octal, which is base 8, and hexadecimal, which is base 16. And we may show some of this later on. Now, when you're working with an int stored in 32 bits, then what you can represent is limited, and it's limited to plus or minus 2 billion, and I've written it out here explicitly. You can go positively up to 2,147,436,647, and your smallest number, your largest negative number, another way to put it, is 2,147,483,648. It's not symmetric because of the fancy way people represent integers on the machine. It's called a 2's complement representation. Typically, the first bit is in fact the bit that affects how you interpret the sign. So you also have these other forms of ints: short, long, and unsigned. Short, it means use less data. Long means use more, a bigger range. So short can mean a smaller range. Typically, you're using fewer bytes. You'll see in a second when I write an example that for my machine, short is 2 bytes, ordinary int is 4 bytes, as we've already said, and then long will be 8 bytes. And then there's a further type, which is called unsigned. And in unsigned, you want the data to only be interpreted as positive. So in effect, if you have 4 bytes and you only interpret it as positive, you now have a range from 0 to a little more than 4 billion. So again, this can be very helpful, and it also can mean in a domain where you don't need negative integers, you have an ability to use the machine to work only with that type. Now, for each of these types, there's a way to present a constant. And I'm just showing you here, here's 35, that's an ordinary int. Here's 35 long, and it also can be a lowercase l. This is 35 unsigned, which can also be a lowercase u or an uppercase u. And this is 35 unsigned long. So you should have all of these available on your machine. This is quite important to know which type you're using, both for input and output, because in input and output, the different types take different formats. And you may find yourself mixing the types. And if you mix the types, you have to know what domain you're in, and you have to know how the operations affect values taken from that domain. So a classic problem in programming with a language like C is the fact that the operator divide can be either an integer operator or a floating point operator. And if you have 2 integers, it's 2 divided by 3, which is 0. There's no remainder. If it was 2.0 divided by 3, or 2.0 divided by 3.0, or 2 divided by 3.0, where one of the arguments or both the arguments are double, then indeed you would be in the floating point type. You would have a type of float or double, and your result would be 0.666. So this mistake gets made often when you are thinking you want to do something like average over some integer data, and you forget that dividing can be either an integer operation or a floating point operation. You can get a mistake. Okay, let's look at some code. So here's some code that I wrote to illustrate some of these ideas. And you can play with code like this. You should play with code like this if these ideas are novel to you. And you should extend it. And you can see in this code, I have a short. Short's a keyword. It really means short int. I could say short int, by just saying short. I'm typing less. So here's my variable name, and I assign it a 5. Here's a normal integer, int normal a, and I've assigned it 67. Here's an unsigned integer, and I use in that literal 67 to have a U, this is a long, and again, in order to make sure that the literal is in the right domain, I say 67L. And then here I'm doing some things to show you what the effects of using that. So here's that divide by 2 problem, where at first I divide by integer 2, and then I'll divide by floating point 2, and you'll see a difference show up. You'll also see that here, for short, I use the format HD, whereas normally I could have just used D. And here's another weird place where you'll see that the use of the format type will affect how something is represented. So 67, which is the value of normal A, when presented with the format type C, should show up as some kind of character. We'll see it in the ASCII table. And here is where we can print on my machine, because this is a dynamic operation where size of looks up the type and says a short A, which is type short, what size is being stored in on this machine under this system. And we'll see those values as well. Let me run that. And there we are. Short A was 5, divide by integer 2, and we get not 2.5, but 2. But short A divided by the float 2, that should be 2.0, will be 2.5. 67, as interpreted as a character from the ASCII table, would be a capital C. And then sizes in the bytes on my machines are 244. The second 4 is for unsigned, and then the biggest is long, which all makes sense. The next data type we're going to talk about are the floating point numbers. As you can see with the little sea turtle, he's really happy when he's floating in the sea. So here are the float types in C. Float, double, and long double. And these are 3 types that are usually ordered in shortest to longest. And we'll see there is a catch here that's not guaranteed. So the shortest is float, and its range is typically from 10 to the minus 38, a pretty small number, to 10 to the positive 38, pretty large number. For example, scientists think that the universe is something like 10 to the 88th atoms. So that's an even larger number, but this is still pretty significant. For example, on Earth, there's something like 7 times 10 to the 9th people, or 7 billion people. And then that can be expressed with 6 significant figures, as in 0.123456, and then there's an exponent part, which is 10 to the 12th. And showing the exponent part of the float, we use an E. So this is a general way to write the integer part, the fractional part, the exponent, and then a plus or minus integer here. And you can consider that there's a sign of the entire floating point number, a fraction, and the exponent. Now, if we go to, on most machines, a longer type, and Typically, again, if you use the size of operator on a float, you'd find mostly that it was 4 bytes, and double you'd find is twice as large, or 8 bytes. And that lets us express more stuff. So one of the things that gets increased is the range. The range becomes from this extremely small number, 10 to the minus 308th, up to a very large number, 10 to the 308th. Then we would have no problem representing the number of atoms in the universe. And we, instead of 6 or 7 significant figures, we typically get 15 significant figures. Finally, we have long double. And long double, when it's implemented and is larger than double, stays with the same exponent range, but it adds a great deal more significant figures. So there's an IBM implementation where there are 31 significant digits. But again, this can be system dependent. So we have, in the C system, these 3 types: float, double, long double. You can declare a variable of any one of these types. The notion is float conserves the most space. Double is typical, so frequently I just use double for most of my things. And long double gets you all this extra significant figure. But the only thing guaranteed by the C compiler is if there's a double, it will be at least as large as float and at least as significant. And if there's a long double, it will be at least as large as double and as significant. So it could conceivably, on some especially early C system, all 3 of these could really mean the same thing. But then on some modern supercomputer, they may also be clearly distinguished in the way we just talked about. Finally, we have to know how to write literals or constants. And here's 3 ways to write the constant 1. Notice 1 is none of that way, so it's not possible. If you write down 1 without a decimal point, that's going to be the integer literal. And we're going to see later, when mixing types, this can be very important. So if we want, we can write 1.0, which is quite clear, or 1 point and not have the fractional part, or we could write 0.1 e of 1, which is another way of saying that's a power of 10, so that would just shift it to 1. And this would be the least confusing, but all of these would lead to the same literal as a float. Now, it's important to understand that significance is critical in a computation. So when you're dealing with these numbers, they are not like real numbers from mathematics. In the world of mathematics, there ostensibly is a place on the real line where you could show pi in all its glory, 3.14159, etc., 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 with as much precision as you want. In a standard representation like a double for pi, you could only get your 6 or 15 significant digits represented as a double. So you're going to lose some precision. And think about where this could show up. You might have a computation which looks okay, like you've added a tenth, the real number a tenth, to the real number 1, 2, 3, by real number I mean double, 123 raised to the 10 to the 12th power. It turns out this number is so large that when that's added in, the result is no change on this number. It's dwarfed by the larger part of the number. So that means this computation, if you put it in some expression, would not have an effect. And in more advanced courses on numerical analysis, people who are specialists in this have to keep track of precision, loss of precision, and some of the precision that may come about because a number that looks like it's precise in decimal might not translate to it being precise under the kind of binary representation that's used for a floating point number. So something like 1 1/3, 1.33333, might not have the same kind of precision when it's translated to the internal number. Okay, finally, we also want to know how to do input and output with these floats. So that means we want to know about conversion characters, and we have a selection of conversion characters available. We can use percent lowercase e or percent uppercase e, and then it prints as a number with a fraction and an exponent part. Or we can have a percent f and it prints as a number written out but without the exponent. Finally, we can have a more flexible format, which is percent G or percent uppercase G, and they pick from E or F and decide on which one to use based on what gives you the shortest representation. So this is more flexible, but you might end up with one or the other, depending on which is shortest on printing to the screen. Okay, in the next segment, I'm going to use some of those ideas and actually write a little piece of code to show some of those ideas and get you used to printing doubles and also to using the math library, which has functions like square root and sine. So you might look online to do a little work on how the math library can be used. Okay, in the next program, we're going to continue with understanding how to write expressions that change the flow of control. So we're going to continue to use the if-else logic, but we're going to change the kind of expression we test for. And the kind of expression we will test for is a logical AND expression. So you'll see in the heading here, this program is about logical operators and, to understand them properly, short circuit evaluation. This is a program that's going to tell us whether to take an umbrella when we go outside or not. So first off, we have to know whether we're outside. We don't need an umbrella on the inside, and we have to know weather, and we're just going to use very simple values for whether we're inside or outside. Outside is going to be assigned 1 if we're outside, 0 if we're inside. Weather is going to be assigned 1 if it's raining, and 0 if it's not raining. So in the program, we're asking the user, tell us whether you're inside or outside. enter if outside 1, 1 representing true, 0 representing false. So recall, in an expression in which you test for, in effect, true or false, what you're really testing for is 0 and non-zero. So 0 represents false, 1 represents true. And the same is going to be the case for the variable weather. So here we ask for the weather. And then depending on whether we're outside and whether it's raining, we're going to write, please use an umbrella or dress normally. Well, if you recall anything about elementary logic, the only time a logical and statement is true, where there are two clauses, A and B, is when both clauses are true. So outside has to be true, namely 1. Weather has to be 1, namely rain. And only then would you printf, please use an umbrella. The other 3 cases all involve dress normally. So you should try to review that or make sense out of that if you're not familiar with that. Now, we're going to talk about a very interesting efficiency hack in the C programming language, which is, in this expression, if outside is false, namely 0, then it doesn't matter what weather is. We're going to dress normally. So when outside is false, the expression is already false. So that means the else, dress normally, will be printed. That's called short circuit evaluation. Imagine that these two things are very complicated expressions. Then they actually would save you a lot of computation. Again, this is the idea behind short circuit evaluation. You needn't evaluate this part of the expression if the first part of the expression already determines the result. I want to look at some detail. And the detail is how to evaluate A and B. And this is just a review, hopefully. And in logic, there are 4 cases. The A can be true, the B can be true, the A can be true, the B can be false, the A can be false, the B can be true. This is what's called a truth table. And finally, both arguments are false. The result true, false, false, false. And again, if you recall, on short circuit evaluation, anytime the first argument determines the overall result, in this case, when the first argument evaluates the false, we needn't evaluate the second argument. So we avoid evaluating the second argument. That's called short circuit evaluation. One last thing about this operator is its precedence. Very low. And I'm going to go over the whole precedence table, but by very low, I mean it's below any kind of mathematical expression. So if there's a mathematical expression involved in these arguments, then they would be evaluated before the logical and get evaluated. Okay, we're going to have our first example of a nonlinear program. So far, the programs we've been writing and executing are do the first line, then do the second line, then do the third line, keep going until you do a return of 0, and you end the program. Not all programs can be that simple, so it's very useful to have the ability to test something and then decide whether to do one of a number of things. A simple one would be one of two alternatives, and that's what we're going to study right now. And later we'll also study how to do things that are looping as well. But this is fundamental. We're going to either do action 1 or action 2, but not both. So this is our first program to use an if statement. So looking at the program, we have what's an if-else statement at the heart of what we're doing. And the program is very simple. It asks the user for a speed. It asks you to enter your speed as an integer. And then, depending on what it sees as your speed, it executes that and says you have no speeding ticket or a speeding ticket. And I think I've already compiled this. Let's just make sure. So it says enter your speed as an integer down at the bottom, and let's say my speed is 78. Sure enough, I get a speeding ticket. Now let me do that again. It says enter my speed as an integer. I say 62, and it says no speeding ticket. Okay, let's go into more detail on the qualities you get in using how to properly use this kind of if-else expression. So the program, which I just called the file is C4E week 3 P1 dash if. And we can see how to use an if-else. The critical thing is the general syntax for it is if expression in between parentheses, then you do what I will call the true statement, else you'll do what I call the false statement. And these expressions can be arbitrary, but they're frequently what we'll call relational. So the expression gets evaluated, and if it sees a value of 0, it thinks false, and if it sees a value that's non-zero, it thinks true. And in the program we just wrote, the relation was speed less than 65. And for example, if you had entered for the speed 50, then that would be less than 65, then that was true, which means that that expression evaluates to 1, which means that the printf is going to print new line, no speeding ticket. Similarly, if you had a speed, again, this relation, speed less than 65, where you entered exactly 65 or more, then this would not be true. That means the expression would evaluate to 0. That means the false alternative would be taken. That means you would get your speeding ticket. Now this could be altered. What if you made a mistake and you said, no, exactly at 65, you're not speeding. And you see in California, a lot of highways have a 65 maximum. So if you speed at less than or equal to 65. So this is a different relation. It includes 65, and then 65 remains true. The relational operators are 4 of them. Less than, greater than, less than or equal, greater than or equal. And you should be used to them from high school math. It's also important to know their precedence. Their precedence comes out below arithmetic operators. So operators like plus and times and modulo bind more strongly than the relational operators. So that if you saw speed less than 65 plus I, the sub-expression 65 plus I would go first. That would be done. That addition would be done. It would be as if you had parenthesized this. You don't need to, but you have to understand what precedence is. It's probably a little clearer to do the parenthesization, but that means this plus is done first, so you'd add an I, then you would do speed. So I might be some increment where the highway police gives you leeway. And so maybe typically in your neighborhood that's 4 more miles. So that kind of increment might be more realistic about when you got a speeding ticket. All right, so the very elementary program, you should get out of it how to use an if-else. By the way, a simpler kind of statement is just an if. And in the if statement, you have if expression, and then you execute the statement if it's true. So if you have an expression that evaluates 0, then you omit the statement. And indeed, you could have turned that if-else into 2 if statements, but that would be not as elegant and also somewhat inefficient because you would be evaluating the relation speed less than 65 twice. So in this topic, we're going to deal with iteration. Iteration is critical to computation being useful. If everything was simple and a few lines of direction where we could finish them one step at a time, we largely wouldn't need computers. The reason computers are so powerful is they can do trillions or millions of trillions of operations in a relatively short time, which is impossible for humans or even humans aided with mechanical calculators to do. So this is a true critical topic, and if you master this topic, you have an enormous amount of the utility of writing code and programming. And here we're going to study the while statement. The while statement is fundamental. It's the simplest form of iteration statement. We're going to see in a little bit a more sophisticated form, which will be the for statement. But it's best to understand the while statement. That'll make it very easy to understand the for statement as well. So the while is syntactically while paren with some expression, close paren with some statement. And most normally that statement is what's called a block or compound statement. Namely, it's really a statement that is an open brace and a closed brace with a bunch of statements in between. So you can do more than one statement action. That makes it very useful. Here are the semantics. What we do is we check first to see if the expression is 0. If the expression is 0, the statement is not done. It's omitted, and we just skip to whatever is next. We can think of that as false, though really in C, false is 0 and true is non-zero. However, if the expression is non-zero, then we execute the statement that's sitting under the while, and then we repeat. We go back and ask, is the expression 0? We continue. And that just keeps going until we see the expression is 0. Here's an example. While I less than 10, So that kind of expression is relational expression. So that is frequently what we'll see as a test. And also, this is idiomatic in the sense that very frequently in an iteration you do something that is involved counting, and counting normally uses integer variables. So in this case, I is assumed to have been declared as an int of some value, typically less than 10, otherwise this wouldn't be executed. And we'll check. If I is less than 10, then we continue into this compound or block statement. We do the printf, I equals, and we print out the current value of I. And then, again, very common in iterative statements is we see an auto increment of I. So here's auto increment of I. We add 1 to it. Why? Because we want repeated behavior, but ultimately we want to exit the loop. So let's say I starts at 0. We will print 0, and then we will print 1, then we will print 2, and so forth, until I hits 10, and then we will stop. So this is canonically a very simple loop, but it still has many of the characteristics of even the most sophisticated loop has. There's something where there might be a counting variable. There's some action. This may be actually a whole series of actions, a series of calculations. And this just goes on and on until we exit this loop. In the old days, we used to exhibit this behavior what we called a flow chart. So here's a flow chart for this while loop. We have a test. The test is false. This is the false part. Let me indicate that. So false again, keep in mind false is 0. And otherwise, non-false, we execute. Non-zero. So the statement, often a compound statement, and then we go back from here and retest whatever this test expression is. In that case, it was I less than 10 in that example. So we enter the loop, that's the while statement, we do a test, we either exit when false or we continue and do some execution, and then we loop, test, exit maybe, if not exit, repeat, and keep going. If we avoid exiting, we get into what is called an infinite loop, and that's something that you would have to make sure you don't want. It eats up computer time, and generally speaking, it means you've created an error in your program. Okay, we've completed explaining some of the critical details of this code, but now let's see the code in detail and make sure it works. So we're going to create a variable for each kind of item, each character we're trying to count, blanks, digits, letters, others. Since we don't have a count yet, all of them will be initialized to 0. And then we're going to use C to indicate the integer value of the character. And remember, characters are ordinary C are somewhere between 0 and 127, and that's the standard ASCII character table, which you should get familiar with if you haven't until now. And this is a very convenient thing we're going to find from the standard library. We can find it in standard I/O, and that is the getChar function. No arguments, and what it does is it obtains from standard input which is in this case going to end up being a file because we're going to redirect. But it could also be a typing from the keyboard if we don't do redirection. And here we test to see if we're at the end of file, and this is C, meaning end of file, and that's a constant. It's typically -1, but it's a previously defined constant, which is a special value that would otherwise not be in the file. So -1 is outside the range of the ASCII characters. And we're just continuing that iteration, that loop, until we hit the end of file. Here we see a complex if-else-if statement inside the while loop. Notice I've made the while loop a compound statement, but that was unnecessary. It's just stylistically nice, even though this is actually a single if-else statement, so it was unnecessary. Here's if C equal blanks, then we auto increment blanks. If it isn't a blank, we test to see if it's the integers between 0 and 9. And that range is strictly, if you go to the ASCII table, strictly those values. And here is a more complicated expression. I'll talk a little bit about it. It's the lowercase letters, but somewhere else are the uppercase letters. So we couldn't just say if C, lowercase a up to Z, so there'd be a lot of stuff in between. But these are all contiguous. Again, the only way you know that is by looking at it in the ASCII table. So this is one range. And also, you'll notice that the double ampersand is logical and that takes precedence over the double single bar, which is the logical or. So this sub-expression gets done first. If that's true, then this doesn't get done. Again, the way these expressions work, this is what's called short circuit evaluation. You could look that up if you don't remember an explanation. It just means we only need to test this if it's true. Then an or expression will always be true. If this fails, then we have to test the second part. And similarly, short circuit works with the and parts. If this part is false, then this little part is false, then it fails for the entire expression. That's called short circuit, so we don't have to do the extra work. And we have blanks incremented, digits incremented, letters incremented, others. And you can do something even more elaborate if you had some interest in developing this program further. And then here we just print out their values. So I'm going to run this program. As I showed in the previous segment, I'm going to use redirection. And I'm going to run it on a file, which indeed is the program you saw at the beginning. And that program had 196 blanks, 17 digits, 302 letters, and otherwise had 152 other things sitting in as characters, which could include things like new lines and tabs. So they could be non-printable characters as well as printable characters. We're going to do more with the while loop because it's so central to iteration. And we're going to show a simple program in this segment, and then we're going to go on to show more complicated programs in the next segment, and then we will do a bit of a quiz. So in the following program, I'm going to write an iteration that's going to ask a question. This is what I call my Valentine's Day program. So put your loved one in front of the screen, and then start your executable, and it'll ask you how much you love that person. And then depending on a score, what you input, it will print out your Valentine's message. So you can see that I just want to emphasize, and that's where repetition is going to come in. I'm going to emphasize how much I love you. And this program's dedicated to my wife. So let's look at some critical parts of the program. First off, there's going to be this declaration for the integer repeat, and that's going to tell us how often the loop is to be repeated. Now, the while loop is the fundamental loop. It's the simplest form of loop in the C language. Later, we're going to see a more sophisticated form of loop for. But if you understand the while loop, in fact, you can do everything with the while loop that you can do with the for loop. It just requires a little more, a few more statements. So the integer repeat is going to be a repetition. Now, here's where we're asking how much I love you. That can be changed. You can try to write your own version of this. Here's our input. Of course, idiomatically, we have to ask for the address of repeat, and we're expecting input between 1 and 10. And now we're going to print out I love you very, and here is the actual loop construction. Here is your comparison statement. So repeat, as long as it's greater than 0, will continue. When it's equal to or less than 0, then this will terminate. We check repeat, it was 0, but here we're going to enter something else. Ostensibly, it's going to be between 1 and 10. So for example, if it was 1, 1 is greater than 0, and then we're going to print very, and then we're going to decrement, the auto-decrement of repeat. This is very common. Something to iterate on, something to either auto-decrement or auto-increment, and so the loop ultimately would stop, because if we enter a number, whatever, a positive integer, this will ultimately reach 0. If we enter a negative integer or 0, then it will stop immediately, and then we end with print much. Let's execute this program. I already compiled it. It says, how strong is your love? I'm going to put in 10. Voila. I love you very, 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 very much. I think that should be your goal. Let's try one more time. What if I put 0 in there? It just prints it that once, even though it said how strong is your love. So I didn't really test for this. Indeed, I can use out-of-range values. I didn't intend to, and then you get an even longer thing. And of course, if I use the value 1, I get 1 very. All right. So try and play with such a program, or write your own version of that program for Valentine's Day, and we'll go on to something more elaborate. Okay, we have been through while loops, and now we're going to go to a slightly more sophisticated looping statement called the for loop. Now, a for loop acts very much like the while, but is more compact. And you can visualize it as enter the loop, do a test. If you get a 0 value, you exit and do a next statement. Otherwise, you execute the looping statement, go back, test, loop, test until you get the 0 value and exit. Here's a simple example of what the for loop looks like. For parentheses, so this is a keyword, parentheses, I replaced by 1 semicolon, I less than or equal 5 semicolon, I plus plus. So it's an auto increment, closed paren. So there are going to be 3 what are expressions sitting inside this parentheses. And then you have the statement you're executing. In this case, we're going to say print count the integer sheep and go to a new line. And that's what's going to be done throughout. And again, it's conceptually simple. Basically, this loop starts where I is 1, and we test, is I yet 5? If I isn't yet 5, we execute this. So the first time through, we're going to say count 1 sheep, and then we're going to, at the end, just before we retest, we do this auto increment. So I becomes 2. We would do a new test. We don't go back to the statement. This is only done one time on entry. This is done each time. This is done each time through the loop. So what are we going to see? We're going to see count 1 sheep, count 2 sheep, and the exit condition is when I is 5, when I is greater than 5. So we will go up to count 5 sheep, and then we won't, at I equals 6, we will skip, and then we'll have to do the next statement. Okay, so that was a simple for statement. Now let's look at the general syntax of that for statement. Keyword for, expression 1, semicolon, expression 2, semicolon, and then expression 3. And then the statement that's being executed, which frequently is a compound statement, again, or a block, namely some series of statements that are enclosed in braces. E1 is most typically used as an initializer, just like in our simple example. E2 is typically, well, it's always the terminating condition. So if it's going to work and it's going to be over a finite number of times, then this has to terminate. That's where you can make some interesting mistakes and get what's called an infinite loop. So this has to be tested. E3 is typically, again, this is all typical, the typical use is either increment or decrement. So the terminating condition frequently involves mostly an integer expression or variable, and then incrementing that integer or decrementing it leads to a termination condition. And that's how you typically write or use a for statement. The equivalent in the while, so you should be able to do this mapping, is expression 1 gets executed as a statement. Don't forget that was typically your initial statement, like I equals 1, I assigned 1. Then you have while of the expression, so that's why the expression, the test expression for the loop is E2. Then you execute your statement, and then you do what's typically your increment or decrement, E3, inside a compound statement. So you can see why a for statement is simpler. It combines all these elements into that one statement. So something that would be multiple statements becomes syntactically easier to write using the for statement. But either statement can replace the other. Okay, let's do a more detailed example. We're going to assign to a summing variable a sum of 0. We're going to assign to some condition for termination n equals 5. So we can see if we change this, or if we use scanf to get this, we can get a general number here. And then we're going to say for I equal 1, assigned 1, the test is I less than 5. And this is less than, not less than or equal. Auto increment I. So we're going to start with 1. We're going to, of course, count up to 5. So this is going to fail at 5. So we don't have to worry about an infinite loop. And then internally, we're going to do a sum. Sum is going to be replaced by sum plus I. And you should know that this can be done as well with plus assign I. Keep that in mind. And then after the loop, this is not under the loop, and we can show that with this non-indentation, so these are at the same level. We'll print our answer at that point. Now, what will you see executing this? What you're going to see is you will wind up with sum equals 10, I equal 5. Internally, as you go through the loop, the first time sum becomes 1, I is 1. Second time sum becomes 3, I is 2. Third time sum becomes 6, I is 3. The fourth time I becomes 10, sum is 4. And then when I turns into 5, it doesn't get it in. That's the test condition. So we would exit, and that's what we print. Okay, so you should practice with this. Maybe take this very loop, write it inside a real program, place print statements, modify it, and try to do something with not just increment, but decrement. So let's look at a straightforward use of the for statement, and we'll use a program similar to one we wrote for the while statement. In this program, we're going to try to count some of the characters and distinguish some of the characters in a file. Again, later we're going to use redirection. So I'm going to count blanks, and we'll actually apply this to this particular file. So anything that's a blank is something like that would be a blank. Right there. That would be a blank. And we have a lot of blanks just because we like a good layout of the program. Now, we're going to count blanks, digits, total characters, and then again we're going to use the integer variable c to store the next character we select out of the file. And here's some interesting syntax for a for statement. We leave expression 1 empty. Expression 1 would be right there. So all you're seeing is a semicolon. When expression 1 is empty, there is no initialization. We don't need initialization because we've already initialized effectively total characters is what is going to be what's counted. And it's not going to be involved in the termination. The termination is going to work in the same way as it did for the while statement. Namely, C calls this routine out of the standard I/O library. That routine is a get character that normally returns one of the ASCII values. However, there's a special value for the end of file, normally defined as -1. So as long as it doesn't see the end of file, it doesn't exit. And then at the end of each loop on this, total characters would be incremented, having started at 0. So we'll test for blank. There's our blank character. Otherwise, we'll test for digits. And we could do our tests as we did before. So I'll leave it up to you if you want to make this a more elaborate program. And it wasn't necessary, but I did just because it makes it clearer. I made this is indeed a single statement. This is an if-else single statement, so it would not need to be encapsulated as a compound statement. But sometimes that's just good practice. It makes sure you're aligned. Notice that since there's an inner loop here, I use typically 3 spaces, so people use 4 or 5, and frequently they use the tab character. And they indent to show the level of flow of control. So the for statement is controlling the if statement. The if statement is controlling this substatement that increments blanks. And the else if is controlling the substatement that increments digits. When we exit the loop, namely when we achieve an end of file, then we can print out our totals. So let's show that this works. I'm going to, as I say, redirect the file that I just typed, which was, I believe, if I've got this right, C4. And sure enough, there are 141 characters, 16 blanks, and total characters were 543. If you want, we can go back and look at that program. But we said there were 16 digits. Maybe we should just check that to make sure we didn't make a mistake. Whoop. Okay, so there was 1 digit, 2 digits, 3 digits, 4 digits, 5 digits, 6 digits, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So indeed, our program seemed to have worked correctly. Okay, so I would suggest that you try and write this program for yourself and make it more elaborate. In this segment, we're going to look at 2 of the more oddball operators we have in the C language. The first of them is the conditional operator. It's question mark colon. The second one is the comma operator. Again, as with lots of things in C, things get overused. So comma can occur in many places. It's not always a comma operator. Sometimes it's a list separator. And question mark can be something elsewhere, and question mark colon, the conditional operator, is uniquely the only ternary operator. So here's an example of use of the question colon mark, and the syntax in this example is C assigned A less than B, which is a relational expression. Remember, it will evaluate to 0 or 1, true or false. Well, 0 is false, 1 is true. And depending on which, that's the question mark, if it's true, the value of the expression is A. And if it's false, the value of the expression is B. And we can express this as an ordinary if, then, else. So if we wanted to, we could avoid the ternary operator. And it just means if A less than B, then C is replaced by A, else C is replaced by B. So notationally, we have a ternary operator, which saves us a lot of writing. So that's what you might say. It's big value, it's terse, it's concise. The general syntax is there's an expression, typically the expression that's taken to be 0 and non-zero. Then depending on the expression, it evaluates either expression 1, the true part, or expression 2 here, the false part. Another characteristic of this is it's very low in precedence, so it occurs as one of the last things that would be evaluated. It's the third lowest precedence among the 16 levels of precedence in the language. And it's also unique in that it's the only ternary operator in C. So that's an interesting factoid. On the other hand, the comma operator is written as this: expression 1, comma, expression 2. And its semantics are, first, expression 1 gets evaluated. Only after that does expression 2 get evaluated, and the value of the overall expression is expression 2. And this comma operator is also known as a sequence point. In other words, expression 1 must be operated on first before expression 2 is done. That's very important because C is a language that allows side effects, and the side effects can affect, depending on order of evaluation, what the outcome of the program is. So where you have an operator like A plus B, a symmetric addition operator, binary operator, there may not be a specified order of evaluation, and different compilers may, for optimization purposes, do different orders of evaluation. That's very poor practice. You don't really want a program to be non-portable in that way, but you have to be aware of that as possibly something that would give rise to spurious results. The other thing about this is that it's the lowest precedence operator. So it gets done last, and it's just below the assignment operators or the operator assignment operators. So any of the assignment operators are next to lowest, and as we said, the ternary operator or conditional operator is third lowest. And as I just said, it's a sequence point. Sequence point is also important for the logical and logical or, and it also comes up when you see a semicolon ending a statement. That's always a sequence point. In other words, everything has to be done before you move on to the next statement. Similarly, if you have two expressions in a logical and, the first one must be done first, and then only if the first one is true does the second one get evaluated. Here's an example. C is assigned, A is assigned 0, comma, B is assigned 1. The value of this parenthesized expression ends up being 1. So if we use this printf, we would see 1. We would have, as a side effect, A assigned 0. Now, that seems like sort of a weird thing to want, but it does come in useful. Idiomatically, the place you see this most and where it's acceptable is in for statements. So you might see an expression like for some comma 0 equal assign 0, I assign 1. So you might want to assign several things at the beginning of a loop. And then you test for the terminating condition, in this case, I less than or equal to 50. And here's your final step in each iteration where you're incrementing I. And you can see that this for statement is going to be a sum in which ultimately you'll add up. Well, what does the for loop do? Let me give you a few seconds here to think about it yourself. Okay, time's up. Should have been obvious. Sum was initialized to 0, I to 1, and then by the end of the loop, we'll have summed 1 to 50. And this is a standard idiom for initializing for loops. Okay, fini. Okay, let's look at some code where we use the ternary operator. So this code is like a previous program where we were checking on a speeding car and we wanted to know whether there was a speeding ticket, and if it was a speeding ticket, was an ordinary one or an expensive one. But in the earlier version, we had 3 values, and if we didn't give those exact values, the case in the switch would be to default, and it would give us an incorrect speed. But we know that normally when we're speeding, there are ranges. And there's a range. If you go less than 65 or 65, you're not speeding. If you go over 65 but less than 70, you're speeding but not excessively. And then if you go over 70, you're speeding excessively, regardless of your speed. And that's what we're going to do. We're going to turn the earlier program into one that's a little more flexible using a nested ternary operator, just to show you the convenience and how nice and expressive the ternary operator can be. So just as before, we ask the user to print in a speed. After we get the speed, we check to see if the speed is less than 65. And if it is, if the true part is, then we return 65. And that would be a case where we get no speeding ticket. So any value under 65 will yield no speeding ticket. If the speed isn't less than 65 or equal to it, then we would check to see if it's less than or equal to 70. If it is, we return 70. That will be used for our case label, and then we'll print a normal speeding ticket. And otherwise, we'll return 90, and that will be an expensive speeding ticket. And notice, if we've done this all correctly, there would be no need to use the default. Now, you might want to modify this program. That would be an interesting exercise to show what happens if the speed is less than 0. That would be an incorrect speed. Maybe you could modify this so that the default would show up if one of these cases wasn't right. Now, let's run the program just to test it out. You can see on the bottom, we're going to enter speed. If I had 45, there was no speeding ticket. If I run the program again, and I give it 98, there is a speeding ticket, and it's an expensive one. Just to test the last case, we'll do 66. And that was a normal speeding ticket. Okay, and that was a small program showing how to use the ternary operator. The next flow of control statement that we're going to look at is called a switch statement. At one level, it's a bit of a generalization of an if-then-else, because you can accomplish pretty much the same thing with an if-then-else. But structurally, for certain particular control flow, the switch statement is more elegant, and the code that you obtain is more readable. So in a switch statement, basically you switch on an integral expression. So a simple one might be the integer I, and then you have a bunch of cases. And those cases can be critical cases where you want to do different things depending on some small value of I. So let's look at an example. Here's an example. We have the keyword switch. Then we have an integer expression I, which would have to have a value before we enter here. And then we have what effectively are three cases. We have case, a keyword, with an integer constant. So in this case, it's the constant 1, a colon, and then we have a series of statements that will get executed if I was equal to 1. In this case, we have a simple assignment statement, A equals 2 times I. And then we have this special flow of control statement, break. And what break means is if you get here, jump to the next statement that goes after this closing brace. And this is idiomatic. If you didn't have the break here, you would have what's called fall-through semantics. So imagine if break was no longer here. Then you would execute case 2, and there you would have A assigned 3 times I, at which point you'd have a break. Okay, so here the notion is there are three things we want to do. Either I is 1, I is 2, or I is some other value. For another value, there's the special keyword which constitutes everything else, called a default, colon, and again you have some series of statements, in this case a single statement, and then you fall out of the case. So what you're looking at syntactically is switch, an integral expression, can't be floating point, it must be integral, but it could be something like a short or a long int or a ASCII value for a character. And then you have the series of cases that are going to be enclosed in these braces. And the braces sort of act like a block. And the cases act what we call case labels. They basically tell you the switch jumps to 1 of a number. And if that expression is not seen in this list, then you go to the default. If there is no default, then you just don't do anything and you leave. So normally, idiomatically again, you would typically have cases delineated by breaks and then finally a default. That is your standard switch statement. Okay, now we're going to start one of the most important topics in this whole course, and that's functions. A reference, if you're following the textbook, is chapter 5, especially 5.1. So here's a quote. "The paragraph of coding is a function, Dr. P." We already have used functions all along. We started with our basic beginning program with the function int main paren void paren. And inside that function, which was a function with an open brace, was the start of the executable program. We've also used standard I/O, which had functions like printf and scanf, and it was, again, an integer function, printf, and it could have many arguments, actually a variable number of arguments. We've also used a pseudo-random number generator function, int_rand, and others. Why are functions so important? They're in effect a paragraph. If you can write a paragraph, you can write an essay. If you can write an essay, you can write a book. So structurally, the paragraph is a big jump. It takes you from the single correct sentence to a coherent set of thoughts. The same is true for a function. It takes you from a single statement, understanding that statement like an assignment statement, or like a call on a function such as printf, and putting it together to achieve some purpose, some coherent purpose. Functions are important because they are crucial to the reuse of code. They're especially crucial if they exist in libraries like standardIO.h, standardlib.h. These are universally useful libraries, and we don't have to rewrite them. So we have to understand how to use them. And indeed, to be a good coder, we have to know how we should be writing code that's reusable. They're a fundamental encapsulation technique. When you have a big piece of code, and nowadays code can be in the tens or even hundreds of millions of lines to produce a big system, you don't start on that all by itself. You break it up into smaller and smaller pieces. That's called a small pieces encapsulation. A function is a form of encapsulation. It allows you to structure a big piece of code. You structure it into a bunch of functions. Functions call other functions, and then finally you have the overall function main. Here are some things you should think about when writing functions. A function largely should be able to do one thing well. Think of rand, think of printf, think of square root. These do one thing. They don't do multiple things. You don't have a function that does both square root and cube root. You keep those things separate. Functions, when written, should stay with one page of code. Why? Because that's like a paragraph. It's easy to understand and it's easy to test. So a function is a unit that you can manage to test effectively. And sometimes we want what are called preconditions and postconditions. If we have the right kind of input, we should get the expected output, and that should be something we can properly test. Here's our syntax for a function. We have a type such as int or void. We have a function name, and the function name is a form of documentation like printf or rand or main. Then we have a parameter list. This can be an arbitrary comma-separated list. These are the parameters passed in. And you've seen that with, for example, printf. And then you have the body of the function, which is typically this brace and close, what we call block. The block starts with a bunch of declarations if needed, and then a bunch of executable statements. So here's an example, simple example. Void, right address, void, so it returns nothing. It needs no arguments. And we're going to say printf clause, new line, printf North Pole, Santa Claus's address, close brace. So now we've encapsulated this idea and we can use it wherever we need it. This is a function definition. It allows us to call the function. How would we call the function? We would just say write underbar address, paren, semicolon, and one could imagine that's being called inside main, and then this would execute those two printfs. As I said, it acts as a paragraph. The code is needed repeatedly. It abbreviates, makes it easier to test, and makes it easier to understand big pieces of code. Okay, we're going to go on from here and show in a coding window several functions and how they work. So we're beginning the topic of functions, and functions are very important. I just discussed how come they're possibly the most significant topic in this whole course. They basically get you from the level of being able to write a sentence to the level of being able to write a paragraph. And as a consequence, once you can write a good function, you can write any kind of code. So here's a function, of course, it's main. And notice we've done this before. It was to exhibit the use of the while loop. Again, once we learn how to write flow of control statements, they're very critical. Iteration is crucial. The while loop is the simplest form of iteration. This was a program I wrote for my daughter and wife for Valentine's Day. So you're asked how much you're loved, and it repeats and says, I love you very, and then however many times you've asked it to repeat, you say very, very, very much. Now, a crucial part of this, and if I wanted to reuse it in other code, is this little for loop. So I'm going to encapsulate it as a function. All right, so let's look at the function version of the same code. So here we've written our function. This first part of the function, this is a function definition because it includes how the function is declared and what its meaning is, what its code is. If we just had this first part with a semicolon, that would be a function declaration. That would also be known as, this part is known as a signature. Its signature is, what are its characteristics? What is its return type? What are the arguments that are being passed in? And its name. So this is an open brace. We could have declarations here, but we don't need them for this simple function. And there's our code again, while count being passed in. And we end up executing that. And now, look how much simpler, and in fact, it even aids the documentation, it aids in the debugging of the program, where inside main, which is a second function, we call this function, write, vary, repeat. So repeat is the actual variable here. It's whatever we entered as value, as. It gets passed as count, and we'll talk a lot more about that later. These are all passed in by value, and they get used locally. So they don't affect the value of repeat. Whatever repeat was, if I put 8 in, even though count goes to 0, repeat later would stay at 8. We'll discuss that in more detail. And you can see, write, vary, repeat, and now we have a much simpler main. So if we nest these functions, if we write a function package to do a complicated program, and then in main we just call them, we have a structure to how to write our code. Very important. Let's just test it out. Okay, I love you very, 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 very much. So play with that program, make sure you understand function encapsulation, and we're going to do more with it in our next discussion. So an important part of understanding functions is the use of the return statement. And the return statement is a flow of control keyword, return. And we've already seen it. We've seen it right from the get-go with our first programs, where we always say at the end of main, return of 0. There's a convention. It can be not used, but it's better style to use it explicitly. So at the end of a function in main, what its meaning is that main returns a value 0, but where does it return it to? Main is the program that you're executing. It returns it to the operating system, and it's used by the operating system sometimes to figure out whether there was an error in the program. So return of 0 means the program finished in an expected orderly way, a normal exit. The syntax of the return statement is either it's return semicolon, no expression, return of semicolon, or it's return of an expression, semicolon. Here are 3 simple examples. They're return of semicolon, return of 0, return of the expression a plus b. Notice, I did not need to parenthesize this, but by parenthesizing I made it clearer. So I could just as well have written zero. I could have parenthesized even a simple integer constant like 0. So people generally, when they're returning an expression, even if they don't need to, because of clarity, stylistically, they do use parenthesization. Let's see a simple use in a function. Here's a function. Self-explanatory. I've called it cube. It means that I'll take a value, which is a double, I'll multiply it 3 times, so I get the cube of the passed-in parameter, x. So double is what's returned. That's the appropriate value. If these do not line up, if this expression is not double, then there's going to be some kind of conversion. Conversion rules can be messy and complicated, and generally you want to avoid conversions, but we will expect a conversion. How can it be used? We can call it like a is replaced by the cube of 3.5. So internally, this gets computed. It's 3.5 times 3.5 times 3.5, and that is the value returned to a. Notice, by the way, just to make that last point clear, if I had said A is returned cube of 3, what actually happens is 3 is an int, converts to double, and A ends up being the double 27.0, not the integer 27. Okay, that's return. Return is fairly simple. Our next topic is function declarations and prototypes. So far, what we've been using is definitions, which are also declarations. But what if main didn't yet see the definition of a function that it's trying to use? You would see an error. For example, you could try to use a printf without sharp include of standard lib. That's not standard lib, of standard io.h. You would get an error that something was undeclared. So we need to know a declaration before we get to use something, including a function. The way to get around that, why you can also declare something first before it's defined, is what's also called a prototype. So we can say double, cube, double, semicolon. That acts as a declaration. And then in main, we can call cube. And there's an expectation that we would have the actual code, the definition, somewhere else. And typically it might be after main. And this would work perfectly fine. Or when we get to very complex programs, we would have multi-file programs. And the definition may also be found in a further file. This definition, or also called a prototype, known as prototype, can be just with the parameter types or with names for the parameters. So you can just say double cube double x, just as well as saying double cube double, leaving off its name. It's also sometimes known as a signature. This becomes important when you move on to languages like Java and C++, which allow what are called overloading of functions, giving functions of the same signature different meanings. Well, of the same name with different signatures, different meanings. Don't worry about that until you get to those, if you're going to move on to C++ in the sequence, you'll find out a lot about that. There's also the special signature for a variable argument list. So as we've already found out, when we call printf, we can give it a format string, and then we can give it a whole bunch of variables. And that, since it's a variable length argument list, can be shown as ... namely the ellipsis argument list. And of course, these things are defined in include standard io.h, and it gets you these declarations, which we've already been using. Okay, let's take some of the ideas we've already been discussing with functions and use them again. more practice. You should practice on your own. In this example, we're going to try to print a table of squares and cubes. And we're going to use some simple functions, just again to structure the code properly. And we're also, of course, going to use the standard I/O functions from standardIO.h, where we'll also get prototypes or function declarations. So here we have what we just discussed about a prototype. We didn't need to include the name of the parameter. We need the type of the parameter. So we know from the point of view of main, which is going to use this, it understands that it needs to call a function whose name is square, which returns a double, and which computes a double. That's all it needs to understand how to compile that, as long as it can find the definition of square at a later point, either in the same file or brought in from some outside file. We'll learn later how to include our own coding files, for example. Here's main. Here is where main is going to make use of square and cube. And you notice we have a nested for statement. Let's look at that briefly, just to remind you of why a computer can be so powerful. It gets you to do a lot of computations trivially, just a little bit of writing. So here we're going to say from 1 to how many. That's how long the table is going to be. And we're going to want to write out cubes and squares at intervals of 0.1. So we're going to say, we're going to ask about square and cubes by interval of 0.1. We're going to ask for n. So we will have a table from 1 to whatever n is, 0.9, and print out the squares and the cubes. So this is the outer loop. This is the inner loop. We're doing it in tenths. If we want to do it in hundredths, this would be 100. So again, very simple structure, but very powerful. We get this double loop, and we're going to print where the evaluation occurs and the square and the cube. And of course, this could be extended if we had other things we wanted to compute for that number. And then go down to the end of the file. And here's the actual definitions. So at the front, these things were prototype, but no definition yet. Here's the definition. So now the compiler knows, oh, that's how I define this function called square. Let's go and run it. I want square and cube for 1 to n. Let's just do 2. You can see I get a nice table. 1 squared is 1, 1 cubed is 1, 1.5, 1.5 squared is 2.25, cubed is 3.375, and here's the square and cubed of 2. It's always good for computer scientists to know everything about powers of 2. So that's 2, 4, 8. What would be next if it was raised to the 4th power? Would be 16. To the 5th power would be 32. And here we're all the way up to 2.9. Okay, so that shows you how, in a standard program, we would package it, divide and conquer, write our individual routines, declare them before you use them, and then have their definitions. Either style, by the way, is okay. We could have as a style the declaration and definition in front of main if appropriate. Our next topic is function invocation and the notion of call by value for the parameters. And this is an extremely important topic. So this is central, so you really have to work at understanding this. And as you see, there's a reference, if you're following in a text, 5.7. So we're going to look at how parameters behave, and they behave, or arguments behave, they behave call by value. Here's a simple function. Int compute sum to n, one argument, one parameter, int n, semicolon. The body of the function is an internal local variable, sum equals 0. And then we have this for loop. Notice we don't have a beginning part. That means nothing is done at the beginning. Our testing part is when n stays greater than 0, and we decrement n. So we're expecting to pass a positive value, and we're going to sum all of the integers up to n, and then return that sum. Notice, internally, it seems like n is being reduced to 0, right? So if n started at 20, this is going to count down to 0. What we're going to see is in the external or calling environment, the actual parameter, the actual variable passed in here, if it is a variable, is unchanged. So imagine that we call this function with an integer m equals 5. And we want to compute the sum to n of 5. And indeed, what should be the answer? It should be 1 plus 2 plus 3 plus 4 plus 5. And you should try this out. When we invoke that function, when that function is called, here are the semantics. Here is the meaning of that function. Here is how that function is executed. Each expression in the argument list, parameters, is evaluated. So in this case, it's simple. M was 5. But it could have been something else. It could have been 5 plus m plus 2.5, or 3 times m. Or it could have just been an actual value passed in. All of those would be appropriate. What happens is, whatever that value is, it has to be converted, if necessary, to the type of the parameter. In that case, the parameter was an integer parameter. Now, for m already 5 and an integer parameter, there would be no conversion. But it turns out we could have used an expression that would have been double. We could have used 3.5 times m, in which case the answer would have been 17.5. And in that conversion, it gets lopped off to 17. Again, you might want to try this in your own code if you don't believe it. But you have to understand the whole character of both implicit and explicit conversions between types. So this is one place where you're going to get the possibility of conversions, very similar to conversions you'd get in an assignment expression, where the left side expression is converted to the right side type. Now, this is where it's saying is a very important step, call by value. It's as if for n, remember that parameter n, and we write inside the code action on n. Well, if you substitute for n an n local, as if it is what is used inside execution of the function, with the first step being n local is assigned n. Notice whatever n will be as an expression, that is going to have a value be n local. So n is going to be integer. We'd get an expression conversion if whatever gets done there, and then n local is what is used. N is unaffected. The n value is never changed, even if, as in our example, it seems to go to 0. That's not what's going to 0. A local version of it is what's being changed, and that local version has no effect on the surrounding environment, on the environment from where it was called. The rest remains straightforward. The function body is then executed. We look for a return statement, and if the return statement is encountered, the function exits to where the function was called, or where it was invoked. Called, invoked, same thing. If there's a return expression, remember in this case, our example, we have an integer function. So again, whatever the expression is, it has to be, if necessary, converted back to the type of the function, in this case, an integer, and that's what gets used in the calling environment. For example, we could print the value of that function. Finally, if there is no return, it's as if a return was implicit in the last statement of the function code block. So even if when you don't see a return, you can imagine a return when you fall off the end of the code for that function. All right, so crucial, very important topic. Play with this idea. Try that particular function, write it up, run it, print various values, see that it all works as we've just described. Our next topic is scope rules. Scope rules involve declarations. The declarations typically occur at the head of blocks. And blocks can exist in different architectures. There can be nested blocks and there can be parallel blocks. We'll see parallel blocks later. Now, inside those blocks, we're going to have nomenclature. We're going to have identifier names. And identifier names can be for both functions and for variables. And what we have to know about them is when they're available, what their lifetime is. And the first thing we're going to look at is something we've already used, and that's basically a simple arrangement. So here, for example, is something fairly simple. Int main void block, we declare I, we initialize it to 5, and now its lifetime begins. So it exists, and we can use it throughout this code. And then we can enter an inner block, and we can declare further variables. For example, you can say int j is assigned I plus 2. So if I had remained 5, now j is 7. And at this point, we could print both I and j. We would get 5 and 7. Now, if we exit this inner block, j lifetime goes away. J disappears. And we see, while for simple variables that isn't critical, other variables that involve large amounts of storage, like very big arrays, this can become critical, and it can be a cause of efficiency of the use of resources, the memory resources. So it becomes important in large-scale programs. And then once again, we're outside this inner block. And here, if we print f of I, we can do it. We can get 5 again. But what we couldn't do is if we tried to print f of j, it no longer exists. It would get a syntax error. More complex situation. Here's an outer block. I is 5. We're allowed to declare an inner block variable of the same name. But what that's going to do is it's going to hide the outer block variable. So the innermost block, and this could go on, we could have them even further nested. This is now thought of as I outer, this is I inner. Anytime there's a reference in here, like if we did a printf here, we would see 7 and 3, not 7 and not 5 and 3. So there isn't a way to look at the outer block. There is, by the way, possibilities of doing that in C++, but not in C. So once you reuse a name, that name, the preference for a name is in whatever is most local, whatever block is most local. Once you get out of here, the outer I is no longer hidden. It can be used. J disappears, the inner I disappears, your lifetime goes away. We have structures that are nested, outer, then we have inner. Inside here we have lifetimes, they go away. Inside here we have lifetimes, and then it goes away. We also have an architecture that's parallel. So if we call that block 1 in parallel with block 2, we have a lifetime for these variables that goes from here to here, and then we have a new set of variables that goes from here to here. Different lifetimes. And of course, there are different lifetimes where we're declaring functions as well. When we invoke a function, we have a lifetime, and it only exists as long as the function is being executed. And keep this in mind, when this set of variables is declared, it's put on something called stack. It's an internal way that the compiler manages storage for these variables. Later, we'll see a different way to manage storage, which will be heap-based. But for the moment, the way we will always manage storage is all related to these blocks and the declarations of things within these blocks. Okay, let's look at some code that shows some of the ideas that we just talked about in storage class. Now, this particular code is not going to be terribly useful. So it's only meant to explore our understanding of the different storage classes. So here's our use of extern. Now we could have just gotten away with saying int reps initialized to 0, but extern is the same thing. In effect, it's saying this item should exist throughout the execution of the code and is available in any of the functions. So it's global. That means F can use it. In fact, we're going to use it right here. We're going to do an assignment. Now here's that use of static. Again, that means this local variable called initialize initial to 0, but every time it's called after that, that value is going to be whatever its last exited value is. And notice we've added 1. So the first time called is going to be 0, but the second time it's going to be 1, the third time it's going to be 2, and so on. And we are going to use it in this expression, and we're going to use this global variable as well. So it's sort of an unusual combination of use of the storage classes, but again, it's just really to show you, if you understand what the lifetime is and the semantics of the storage classes are. Now let's look at main. Main is using this passé keyword, auto. We don't need it, but it can be used, and indeed it just means that I is automatic. Automatic means on entry to main, it gets put on the block and gets used. Here, by the way, const is not a storage class. Const just means that the initial value is to remain that value throughout, so that this value in here cannot be changed. Const is a feature of modern C and C++, which adds to the nature of the typing. So not only do you know that there's an integer, but you know its value shouldn't be changed. Let's go further down, look at the main program. So I was initialized to 1. Const says go up to I less than 10, in effect, because that's going to be 10. So this is going to count from 1 up to 9. Auto increment I. I is in effect a local variable. Reps is a global variable. It's going to print out I in reps. And each time it's also going to call this function. What's the idea? You want to see inside that function that called keeps getting changed. So that function is going to tell you that called is updated. And then you're also going to see that effect when you print up this continually added to reps value of called. So it's confusing. If it's confusing to you, what you should do is take this piece of code and rework it and try to use the ideas, even increase it or add some more functions. Make sure you understand the semantics. That's just going to help you. You're not going to write anything like this. This is merely to explore the meaning and make sure you understand that meaning. So I'm going to execute this, and we're seeing that the first time in, reps had value 0 as expected. F is called with that value. That's its 0th time to be called. I was locally 1. I gets changed to 2. Reps is now 1. I is called the first time. So we get I and reps, well, I and reps are going to diverge because reps is going to become reps plus I. So first off, you get I equals 2, reps is 1, then you're going to add 2, and you're going to get I is incremented. That's just an accident that they're the same. So you get 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15. That's the value of I each time. I is now 6, so 15 plus 6 is 21. I becomes 7, you get 21 plus 7 is 28. I becomes 8, you get 28. Makes it 36. And then you get exiting from the loop when I is finally 9. Everything is called. F has been called actually 9 times. It starts when it's called with the called value being 0, and then F gets called the indexing goes from 0 to 8, so f is actually called 9 times. Okay, so hopefully that didn't confuse you too badly. I probably did. So it's really important to test this out on your own. Okay, the next major topic, and this is one that fascinates a lot of people, is to write programs that are recursive. So we'll look at a very elementary program that does it this way. And then later, in some further segments, we will very much make use of the technique and show you actual code and why you want to write code frequently, recursively. So the big thing about computation, what we know is, well, it's really useful, and it's really useful when you do lots of things over and over again, big things. And that's why iteration is so powerful. And that's why we've paid a lot of attention to statements like the for statement and the while statement. They're very useful. And they're going to be even more useful when we come to our next big topic, which is going to be using them in relation to arrays and very large amounts of data. Okay, so we've seen how to do things repeatedly with iteration. I'm going to show you a simple example of doing that, and then I'm going to show you how the exact same thing can be done recursively. First off, in the iteration, we're going to write this little NASA program, little Cape Kennedy thing, where we have a countdown. We're going to decide that we need a countdown from whatever, some integer, for example, it could be 10. And here's how we might do it iteratively. So we might say while n greater than 0, printf time is, we'd print, for example, if it starts at 10 as 10, then we'd auto decrement, and then we'd keep printing that, so we do 10, 9, 8, 7, 6. The last value we'd print is 1, because after 1 it goes to 0. And then before we exit the routine, we print blast off. That's our iteration. We should be comfortable with doing that. We've already done a number of iterations. Now let's do this recursively, about the simplest recursion I can think of. We're going to call this routine void recursive countdown. Again, it's going to have this integer n, and may again start at 10. In the recursive case, we have a test to see if we're what we're going to call the base case. So if we're at the base case, n equals 0, and we're going to print blast off. If we're not at the base case, then we have to do the recursion. We do an else, printf time is whatever n was, for example, starting at 10, and then we call the function again, the same name function, but now we call it at 1 less. And we're going to keep on doing that. The recursion is going to keep printing this. It's going to do the else part until it reaches a value of 0, called with a value of 0. So it happens repeatedly. You have, as a key idea, a base case, in this case blast off at n equals 0, and then you have a general case, or the recursive case. And in the recursive case, you're doing a print of the time, you're counting 1 less, that's ensuring that it'll terminate, and you're done with understanding the most elementary of recursions. And if you've had some mathematics, if you're on the mathematical side of things, you'll recognize that recursion is very similar to mathematical induction. And one of the nice things about doing things recursively is they may be easier to debug or, in effect, prove correct. They may be more obviously correct. And as I say in the next video, we're going to show some interesting, again, simple but recursive programs. So we explained a very simple idea behind recursion, how recursion can work in place of iteration. Sometimes you should prefer one to the other, but you should know how to work with either scheme. And we're going to show both schemes now in computing n factorial. So n factorial is a mathematical quantity, how to build especially large numbers, and it's defined as 1 times 2 times 3 times 4, etc., up to n. As it then gets large, this gets extremely large. So for that reason, we're going to use the long int, because if we use a shorter int, we can't actually compute it for too long. Actually, long only allows it to work for up to 20. What happens past 20? You get what's called integer overflow. You get results that are incorrect because the number of bits available in a long on most machines is 8 bytes, 64 bits, and so for an integer type, it only able to represent factorial up to 20. So let's look first at something we should be comfortable in. We're going to do factorial iteratively, and we're going to accumulate the answer in the variable sitting there, long f equals 1. And then you're going to see in the iteration, it's your standard iteration. The beginning is at f of I equal 1. I goes up to and equal to n, auto increment I, and accumulate f by multiplying f by I. So you see, after you finish this iteration, you will have multiplied 1 times 2 times 3, etc. by n, the definition of factorial, and then you return f. That's the iteration. That should be straightforward. It should be no problem for you. Now, let's look at the iterative version. This is what's a bit novel. I'm calling it recursive factorial. Again, it's long. Int n doesn't need to be long because we can't, in fact, compute on very large numbers. And we check to see the base case. So here's our base case. N is equal to 1. What we know about when n is equal to 1, the definition of factorial is just 1. So we return 1. But if we don't have the base case, we can count backwards, and just as in our countdown program. Except here, we take recursive factorial of a smaller value times n. So this is the generalized case. This is generally what happens in the inductive case. N times the smaller value of factorial. You need to convince yourself that this gives exactly the same result. And that's what I've done here. In comparing both, I've just asked the user to say how many, and then I first do it iteratively, and then I second do it recursively, just to show that we're going to get the same result. So I've already compiled this. Let's run it. Why don't we do it for small number? So here's your iterative thing. Factorial of 1 is 1. Factorial of 2 is 2. 1 times 2 is 2. Factorial of 3 is 6. And again, you get the same results recursively. Let's do a slightly larger version. Let's do up to 10. And here the numbers start getting big. And you only see, because I didn't have enough screen width, this is the recursive version. You can see the final 10 is the same as this 10. And you can see how they go up. And you can see that since you multiply by 10, that's 10 times larger than that. Just like 3 to 4 is 4 times 6 is 24, 5 times 24 is 120, 620 is 720, 7 times 720 is 5,040, etc. Okay, so that's a very standard example taken from mathematics. You get it straight out of a definition. If you saw a mathematical expression, you frequently see functions of this kind defined inductively or recursively. So there's a natural mapping. It lets you easily and algorithmically transcribe that idea into a recursive function. Okay, we want to examine yet another recursive function. And again, we're going to show how that recursive function can be written iteratively. And we're going to show in this particular example, which is the Fibonacci sequence, it's very famous, that sequence is defined as the nth element of the sequence is equal to the nth minus 1 element of the sequence plus the nth minus 2 element of the sequence, where the sequence initially starts with the 0th element being 0 and the first element being 1. So if you follow this formula, f of 2 would be 0 plus 1, namely 1, and f of 3 would be 1 plus 1, which would be 2, and f of 4 would be 1 plus 2, which would be 3, and so on. And what's interesting is, even though the numbers at the beginning look very small, the sequence grows exponentially. So here's a definition, doing it iteratively. I'm going to use longs because if I want, I can easily write something that exceeds a single precision integer. So I'll start off with f2 equals 0 and f1 equal 1. And here's where I add them together. f2 plus f1 becomes the new f2. And we retain the older value of the sequence in this step. And then after we make the summation, f1 becomes the f older value. And you can go to see and check that that will indeed compute this sequence. And we turn, for n, we have to compute it up until the nth element of the sequence. And then we return f2. So that's an iteration, but if you think about it, the sequence is more naturally defined with a recursion. And here's the recursion. If n is less than or equal to 1, then return n. That means if n is 1, then f of 1, the Fibonacci sequence at 1 is 1. Or if it was 0, the Fibonacci sequence of 0 is 0. and for our purposes, the Fibonacci sequence is only defined on the non-negative integers. Else, return the recursive call of Fibonacci n minus 1 plus a recursive call of Fibonacci n minus 2. So that's where we have a recursion, and indeed both recursions count down. So in each call to this recursive function, we get 2 calls, and so on. So notice, if you have to go very deep in computing Fibonacci of n, you're going to get something like to the nth calls of this sequence in order to do the number of summations that you'll need when you get to a large value of Fibonacci using the recursive formula. And here I'm just going to ask you to print a table. I'm going to print a table with ordinary Fibonacci and recursive Fibonacci. Okay. Oop. I'm going to exit that routine, and now I'm going to execute it. I'm going to do a small value of n just to show us what it is. So, iterative Fibonacci, recursive Fibonacci. Answer 0, 0, 1, 1, 2, 1, 1. The third member of the sequence is 2. The fourth member, 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8, and so on. And works very, very quickly. Let's do it again, though. Let's do it for up to 25. And we've zipped by on our screen a whole bunch of values, and then we can see that 15 is 610 plus 987, so we get 1597. Indeed, both the iterative and recursive give us the same answers as expected. But now let's look at a much larger number. Let's look at 45. Now look what happens. We've hit 40. The screen is slowing down. I'm working on a fairly modern Macintosh. All the answers are jibing. You can add the respective previous two to get this, but whoop, okay. It wasn't large enough. I'm going to do it once again because it started to slow down, but what if I do 50? Now you see at 43, all of a sudden the screen is frozen. We saw that it did 44, and that took a significant number of seconds. And now look at 45, it's still crunching. Crunch, crunch, crunch. No, finished. But you can see a noticeable lengthening of time. Now, I'm not going to let this run any further. I just want you to think about that. I'm going to abort this. So what is going on is on the recursive side, and if I had separated, and you can do this yourself at home, you could separate writing it iteratively from writing it recursively, and you could see you would readily get 45, 46, 50 until you got a number too big for the accuracy of a long integer. But it would run very quickly because it's a simple iteration, and it's just a linear time set of additions in that sequence. On the other hand, calling it recursively means that we're going to ultimately end up with a bunch of ones being added, maybe a bunch of zeros, and those, for example, here we're going to have something like 4 million. So this is 4 million. So this is over 1 billion. And when you have over 1 billion function calls, you have a whole bunch of operations going on the stack, and on calling a function, which is one of the more complex functions at the machine level that can actually take some few, maybe tenths of a millisecond, but still some significant time in relation to the simple calculation you're doing. So that's the pitfall. If you use recursion, it could lead to a significant slow-up, even though on the surface it gives you a more logical, easier to understand program for recursive functions such as Fibonacci. Okay, this is going to be the last major topic of C for Everyone Part A. And it's going to be the topic of how to deal with aggregate data. And after we're done with this topic, you can consider yourself a serious programmer. In some sense, the major programming languages of the first 2 decades of the real use of computers, namely the late 40s through the early 60s, had languages like Fortran and Algol, and these languages basically had, for aggregate data, the array type. So we are going to show how to deal with the simple one-dimensional array type in the C language. Now, so far we had multiple amounts of data. We would have to write out individual declarations. So we'd say something like int a, b, c, and so on for as many variables as we need. Or we could say, if they were somehow related, int a1, a2, a3, etc. But this is too limiting. First off, if we really need to do things for very large data sets, like we have to examine a colony of several thousand elephant seals, as one of our homeworks suggests, to find out their average weight, we don't want to have to write out thousands of individually named variables. They're going to be too hard to process, too limiting. Our way around this is to have the following kind of declaration. Int data, square bracket, 100, square bracket, semicolon. So as with a normal declaration, there's a type. This can be any of the standard types like double, long, char. An identifier that should indicate what we're processing. I'm going to use the generic term in a lot of my examples, data. And then a size, which is an integer constant. It's got to be known at this point, partly because the allocation at this point would frequently be off the stack. When we perform that declaration, this is what the compiler produces for us. We get a one-dimensional array structure whose elements are data of 0, data of 1, data of 2, data of 99. Arrays in C start at 0. Some programming languages started arrays at 1, but 0 is the base address of this array. In some sense, data itself is an address in memory. 0 means the 0th element So it's the index really at the, quote, first element that you're going to use in processing, whereas the last element is going to be whatever that size was. In this case, it had been 100 minus 1. So in effect, these brackets with an index perform an address computation that starts at wherever in memory we have data. A normal cell, like int A, it might be stuck in memory cell 2004, and that's what it refers to. But here we have two parts in the memory calculation, and it's important to understand that this is a way to get what we call an address, because later we're going to talk about the relationship between array and pointer. And for more sophisticated work in the C programming language, you're going to have to understand addressing and pointer. But for very simple things, indexes and arrays are straightforward abstraction. So each of these items can store an int, and most machines that will be 4 bytes. Why is this so useful? Well, most processing is not about processing a few things. It's mostly about storing, retrieving, and processing very large data sets. Data sets that are frequently in the millions. Well, look at this little for statement. For I initialized to 0 or assigned 0, it's not initialized, assigned 0, I less than some size, auto increment I. Turns out we're doing a calculation here. We're summing. We're going to take the sum, it's the old sum plus whatever is in data. So by the time we get through that, we have added up all the data in that collection. Maybe we want to use it for an average, maybe we have other reasons to want to use it. But this doesn't matter. This one statement handles as much data as we have available to us. That's what's so powerful. And consider it as the canonical idiom for treating data when stored in arrays. And as long as you understand this and can make use of this, you're basically going to be a serious programmer. Now we're going to focus on the topic of arrays and how to initialize them, and especially how to deal with the concept of string. String is not a data type in the C language. It's really a series of characters. So a string is really an array of char, and we want to see how to initialize it. Of course, a lot of our interesting examples, including some in the homework, is to make use of working with strings. First, let's deal with the whole concept of array initialization. So we know that when we declare a simple variable, like here int ssn, we can, after the equal sign, which in this case is initialization, give it some appropriate constant value. But what happens when we declare an array? When we declare an array, we're actually declaring a bunch of variables which are indexed. And if we don't have an initializer, again, it becomes uninitialized. In some cases, the system will decide to automatically give you a 0, but you can't necessarily rely on that. But now if you want to give your array specific values, and here you'd have an int array which has 5 elements. Don't forget this means data of 0, data of 1, data of 2, data of 3, and data of 4. Then we can give an appropriate number of comma-separated values in this kind of list, the curly brackets. So in this case, data of 0 would be 1, data of 1 would be 2, data of 4 would be 5. But also, we can abbreviate the list. If we wanted all the elements to be 0, we could just list a single 0. We wouldn't have to list comma-separated list of 0. It turns out that all of the elements will be initialized to this value. And also, we can have an array where we don't specify the size of the array. So we just say int data, unspecified size, initialized by 1, 2, 3. And now the compiler says, there are 3 values. So that means they wanted data, and this would have been equivalent to int data 2. And now data of 0 is 1, data of 1 is 2, data of 2 is 3. Okay, so, and depending on type, we would have such lists. So in doubles, we would have doubles. Now, what about the concept of string? Very, very useful. So we've already had strings. We've used them in things like printf and scanf. But strings are really what you might call concatenated together, sequentially next to each other characters, chars. So this string, AB, denoted by the string constant with the double quotes, is really, in its internal representation, the character A, a char, typically placed in 1 byte, the character B, a char, again in 1 byte, and what we're going to call the sentinel character, we're going to indicate that it's a 0, and it can be also written as single quote, \0, single quote. And the reason for that is if we have single quote 0 single quote, we would not have a true 0. We'd instead have the ASCII value of the character 0. And that isn't a 0. So in order to have a true 0, we have to escape the 0 with this escape character, and then we get a true 0. So anytime you see a series of characters and the last byte being 0, that is an internal representation of an array. Let's look at something. Remember, we can also have an array, str, not give it a length, equal, and we can do this quoted string, and this is equivalent to having a series of inside curly braces, a series of characters. But look, there's a space there, I've drawn it, and a space there. So really, this is a character string that has, this is its first element, the letter A, a space is its second element, the letter B, a space is its fourth element, the letter C, and then implicitly the sentinel characters. So what's that going to mean? That's going to mean, as an internal representation, A, space, B, space, C, 0, the sentinel character 0. So that's really a 6-element char array. That would really have been char str6. Keep in mind that the space, single quoted space, has, in the ASCII table, if you look up the ASCII table value, it's 32. So that's what would actually be stored in here, a binary representation of 32. So STR of 0 would have the A character, STR of 4 would have the C character, and then the final element of the string array, STR of 5, would have the sentinel character 0. I call it a sentinel because when we do a lot of string processing, we generally put in a loop and it searches for the end of string. So that's why we call it a sentinel or sometimes a guard. It's a way to find the end of a string. So this has 6 elements. Okay, now we're going to go on to understanding more sophisticated ways of indexing and looping over arrays. Okay, so now we're going to look at some code that reflects our basic understanding of the single-dimensional array. And this piece of code is to take a bunch of data, in this case a series of grades, that'd be 5 grades for a student, and then see what the student's average is. And you can see that this could apply to as large a size an array as you want. So, first off, we establish the size of the array, and it must be a constant, because when we declare an array this way, it's going to come off the stack, and the array must be a constant. So here's grades. There are going to be 5 of them. And recall that grades of 0 is going to be the first element, and then grades of size -1 is going to be the last element. And then this syntax with the curly braces is a way to initialize this kind of aggregate data structure. So just like you can initialize a single variable, you can initialize an array of whatever size by keeping a comma-separated list of appropriate constant values for that array. And if you don't list 5 of them, let's say you only listed 3, then the last 2 would have been assumed to be 0. Then this is going to be our summing variable, and the reason that it's going to be a double is we want the average to be a floating point number. We don't want a truncation error. I commonly is used as a summation variable, so we don't have to say it. If we could say int index, and maybe that would be more clear, but generally speaking, I, j, k are used as summation variables. Now here is our chief iterative idiom. For I, replaced by 0, start with the lowest element of the array, go up to size, auto-incrementing, and do something. This is the step, the internal step of that iteration. In this case, we're going to print the individual grades. We're going to print them separated by tab values. Then we will jump at 2 lines. Then we will do this further work of doing a summation of all the grades. Again, size could have been arbitrarily large as long as we had enough data. So this program, this simple program, could work for a humongous size of aggregate data. And then after we're done, here's our average, sum over size. So let's see that that can be made to work. I already compiled the program. It's going to be in this grade.exe code. And sure enough, my grades are 78, 67, 92, 83, 88. My average is 81.6. Okay, so once you have that understanding, and you can modify this program, you're nearly a professional coder. I mean, once you can manage aggregate data of any size, especially using the array, you have almost all the tools you need to be a competent programmer. Okay, now we want to get into the weeds. This is a difficult to picture set of ideas. Exactly how is an array stored in memory? And what we have to understand is an array has a place where it's stored, and it starts at what's called its base address. And that's because we want a bunch of elements, so we have to have a place to start, and then it runs contiguously through as much memory as is needed, and that gets allocated automatically in this case by the compiler. So there's some things we don't know explicitly because the compiler is doing it for us. And the array has a very strong relationship with another data type called a pointer. So we're going to start to explore the connection between array, address, and pointer. Now, a simple data type like an integer, when we say integer a inside a block, it means create a variable in memory, and the memory needs to be as many bytes as to store appropriately the values that are allowed for an integer. So an integer on most computers now is stored in 4 bytes. 4 bytes are 32 bits. And if we say something like a is assigned 3, then what that means is in these 4 bytes we put an appropriate representation, binary 3, and it's going to be in some location in memory. And remember, nowadays computer memory involves gigabytes. That's billions of individually addressable cells. So each of the cells in your computer memory has a location, which is basically a number. So for just the sake of having some concrete thing to think about, let's say this is location 7006, and we stored 3 there in this 4-byte set of memory cells. So when we think of a variable, we think of its name. That's how we use it in the code, but we think it has a location in memory, and inside that location is some stored value interpreted as an integer. Way to think about this is think of these things as, imagine a whole bunch of billion, and big computers, it could be hundreds of billions of mailboxes. And in the mailboxes there are specific kinds of values: integers, long integers, doubles, chars. Okay, so that's what we're going to store. We have a mailbox, it has an address, that's a number, and then inside there's something which is represented as a binary set of digits and interpreted as a particular data type. Now when we go over to an array as opposed to a simple variable, so let's say we have the array data 4, it's integer again, and we're going to store, remember we just talked about how we can initialize it. So this represents, instead of a single variable, 4 integer variables. And they start, again, if we view the compiler as having assigned them to the mailbox 7006, well, 2 is put in the mailbox 7006. 4 bytes later, at 7010, we put in 4. And 4 bytes later in 7014, we put 6. 4 bytes later in 7018, we put in 8. So we think of this array as having 4 individual cells, mailboxes, appropriate to that integer data type, meaning we need 4 bytes. And we can think of this as data of 0, data of 1, data of 2. There specifically is data of 3. And if you want to know how that address calculation happened, the address is equal to the base address plus 2 times the length of the 4-byte integers. So if the base address was 7006 and we need to be over here, well, that's 2 times 4, which is 8, so it's going to be 2014. That's an address calculation. So an address calculation for an array in C, base address plus the offset, the index, times the size required, the size in bytes required to store that individual data type. And that's what we mean by address arithmetic. And as I say, if these are unfamiliar notions, they do take getting used to. So it's something that don't worry about if you didn't get it. And some of you may not even need it. You certainly need it if you want to go on and do more computer science-y work. But if you just want to be a simple programmer, it may be enough to just understand that indexing works for you. But really, to get to the next level, you want to really understand the notion of address. Now, there are special variables called pointer variables. They're a derived type, and the type is expressed as follows. You say what the basic type is, in this case it was an integer. Then you use the special star character, the asterisk, and then the variable name. So frequently we'll use P for pointer or PTR. And here we're declaring a variable that can point at something that can store integers, but is in fact an address. So let's say A was an integer variable, a pure integer variable. This is initialization, and we're saying here, initialize this pointer to where A is stored, the address in memory where A is stored. Again, if you think back to my previous example, that would end up being 7006. It's something we don't have to know. The compiler is going to decide on it. The compiler could decide differently at different times in the compilation. So it's not something we worry about. But we have to understand that this is getting the address of this variable. And that address is being stored in P. So we can now think of P, it's this value 7006. What's stored in that area of memory is an integer variable whose value is 3, namely that was what we were thinking of as A. And now we can have as an expression P or star P, and those are two different variables. If we tried to print the value of P, we would get some address. If we were to dereference it, star is a dereferencing. If we were to dereference P, the value there would be the integer value 3. All right, all of that is fairly theoretical, a little hard to get your handle on if you haven't seen these ideas before, because you're really thinking at a machine level. You're thinking what the compiler does for you. But we're going to go ahead, and in the next segment, we're going to write some code that will actually show what these values are. We're going to try to understand it by testing our concept, by actually writing code that prints an address, that prints what's stored at the address, and show that distinction in actual C code. So we're continuing with our understanding of pointers, arrays, and addresses. And what we're trying to show here is that while this topic is truly wonkish, in other words, it gets really into the weeds, very detailed in understanding how code functions at the machine level. Namely, you have to have a really good appreciation of memory as a resource and how it's allocated and how it's addressed. And one way to at least get some exposure to it is play around with code. So I just urge you to write your own variations of what I'm doing, just to make sure you get a real sense of what's going on. And here's a piece of code, and it's largely to understand some of the elements of how an array is laid out and how the machine accesses a memory cell and uses a memory cell in place of a name, and also the contents of the memory cell is yet something else. So in this program, it's a modification of one we earlier used, which was to allocate some grades into an array, and then we're going to sum up and average the grades. The sum variable is going to be a double, and here's where we get into this whole notion of pointer. So here is the pointer declaration. Double asterisk, so that's essentially saying double pointer to sum, and that's initialized to ampersand, which is address of sum. So sum has 0 stored at it. This is some address that at the moment we don't know, but whatever the address is in memory, and I'm going to print that out for you, so you're going to get a sense of this magic number, because it's the compiler that gets to decide where to put things, and that's going to be different from compiler to compiler, machine to machine, and conceivably even from run to run. Because on a big machine, many programs may be running, and there may be different parts of memory that get allocated to a particular program. So again, get used to, again, contextually, star here is not times. It's part of the declaration logic. It means pointer to double. Double star is pointer to double. Int star is pointer to int. Char star is pointer to character, which frequently gives rise to the notion of a string. Here's an ordinary variable, int I, and then we do the same thing we did before, which is calculate the grades, printing them out first, and then summing them, and then printing the average. And after that, we're going to look at where all of these variables are located. So I'm going to print out sum is at %p is the format for a pointer address. And a pointer address on a modern machine is displayed in hexadecimal. So that's not something you're used to. Hexadecimal is a base like base 10, except its base is 16. And because we run out of digits, we only have the normal 10 digits, we use the letters A, B, C, D, E, and F. F, in effect, is 15. But we're also going to print it as a long unsigned. So you'll see it more as an ordinary decimal number. And then we're going to print out the value that's found there. So look at what we're printing. Pointer to sum. So that's the value of pointer to sum is an address where sum itself is placed in memory. And this is the two versions of it. We get both the hexadecimal and the long unsigned. And then we do a dereferencing. Star in this case means dereference this pointer to double, which means look inside it and return a double. So ampersand as an operator back up here means address. Star down here means dereference. And you dereference a pointer variable, and then you get effectively its contents. And what that is going to be is whatever the sum of the grades are. And then we're going to print that stuff out. And then we're going to further print where that array starts. So it says grades are at, and now we're going to also use, instead of hexadecimal, because maybe you're not used to it yet, we're going to use long unsigned, and it says grades go from long unsigned to this long unsigned. And this is the base address of grades where it was stored, and this is the address of the fifth element. And we'll find that it's offset by 20 because each element in grades is an integer which is stored in 4 contiguous bytes. Okay, so let's run that program and see that this all works. And again, I just want you to do your own experimentation. Here were my grades. Here was what the program ordinarily was going to do. This is the average. Sum is at. This 0x is the format for a hexadecimal number. And then we see a 7, an F, which remember is the digit 15, F, 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 5, C, which is the digit, I believe, 12. Or maybe is it C, D, E? Yeah, I think it's 12. And then B is 11, 12, 10. D is 13, 0. And this translates into a long unsigned as this very big number. So that's like the mailbox, that's the address. And stored there is the value 408. Notice 408 is the sum of 78, 67, 92, 83, 88. So indeed, that dereferencing of that pointer actually got us the same thing we would print if we had just printed sum at that point. And now look at how grades are laid out. Notice, let's forget all this beginning stuff because that's too big a number. It's located between 1920 and 1940, where sum was at 1904, and there was a variable like I. So if you think about what was being laid out in memory, there were all these individual variables. One was the variable sum, another was the pointer to some variable, another was I, and those were all 4 bytes. And then you come on where the beginning of grades is. So it all makes sense if you think about where things are laid out in that program. And then it goes up to 1940 because Each individual element is 4 bytes long, and there were 5 elements, so you're adding 20 and you get to the last element. Okay, hopefully that makes sense. If that's too wonkish for you, you can probably skip this idea and still manage most of the work in the class. But if you're going to try to go on and you're going to make a heavy use of C and then finally C++, then this is a subject you want to try to master, and a way to master it is to do your own experiments. Okay, now we'll turn to the topic of call by reference. This is another critical topic. Very important that you get to understand this. And again, it gets to this level of abstraction about pointer, variable, memory address. So you have to have a model of the physical memory of the computer and understand what is going on there, where things are stored, what is an address, what's a value in that address. Now, C, as a language, supports call by value. And if you recall, call by value is where arguments are passed in, possibly variables from the calling environment. Inside the routine, they're manipulated. Inside the function, they're manipulated. But when that function exits, those variables are unchanged. So basically what's being manipulated in call by value is a local instance of where the value argument is initialized. Now, many languages also allow call by reference, but C allows you to, what you might say, simulate it. And the way we're going to simulate it is we're going to have to be able to dereference addresses. That means an address variable, when prefaced by a star, accesses the contents at that address. And to get at a variable, to know its address, we use the ampersand operator. These are both very high precedence operators. And the way we've seen that already is in our use of scanf. So recall, when we say something like scanf, we have a format, for example, getting at an int here, %d, and we use ampersand of size, not size. So we go and take the address of size, and inside there the manipulation occurs where scanf is for input. So whatever size's value on entry was, it can be changed by not manipulating the address of size, that's being called by value, but by manipulating the contents at that address. Okay, so to restate, normally parameters are called by value, but we can pass in an address, not necessarily to a pointer, but an address. And this should really be or a pointer, let me just say. And then we use this mechanism to achieve call by reference. We use call by reference to change values, much as we did with scanf in the calling environment. So let's look at something that would be a function we try to create. We're going to call it a swap function. It has a very simple job. Swap A of B is supposed to exchange values. What A's value was becomes B's value, becomes A's value becomes B's value. So if A started at 2, B started at 5, we want to reverse that. We want B to now be 2 and A to be 5. If we try to write this code as swap into I and j, int temp equals I is replaced by j is replaced by temp. So internally here, the logic is right. The values that come in as I and j internally will be swapped as I and j. But if instead we call these with A and B, we would notice that nothing happened to A and B, so it won't work. It won't work. Hence, we need call by reference. In call by reference, we write the swap function as 2 pointers. Temp is still an int. Temp gets the dereference value of I. The dereference value of I is assigned the dereference of j. The dereference value of j is assigned temp. This will work. That's what we want to do. This is the canonical call by reference function. If you understand this, you'll understand how to write call by reference in the C world. What are the steps? Let's summarize. We declare parameters as a pointer. We use dereference pointers, star p, within the body of the function. Notice how we dereference I and j there. And then we pass in the address of the variables we want the values swapped, just like with scanf. We'll say ampersand of A and ampersand of B, and then it all works. So practice that, write some small functions, make sure you understand how that all works. Now let's turn to some actual code where our parameter will be a one-dimensional array. And this will look familiar because we had a one-dimensional array already in main, and we were doing the same thing. We were printing some grades and then computing an average. So we'll show how to do both things, but now we'll encapsulate as a parameter the grades, and we'll show why this is so effective. So both routines, one will be for getting the average of the grades, the other will be for printing the grades. In getting the average of the grades, we need to know how many grades. And then we're going to pass in the base address of grades. So we're going to assume that if there are 10 grades, then there are going to be 10 entries in the grades array, that everything will be of the appropriate length. That's one place where you can make an error. You can have too many for the array that you're passing in, for example. Locally, we need a counting parameter, int I, and we also need a parameter for adding up the sum of the grades as before. And here again, we see this very natural idiom. For I equals 0, I less than how many, because the array starts from 0. Auto-increment the index, and then create the repeated sum. So you're adding in each element. And it doesn't matter how many elements. So that's why, again, it's so powerful to use a programming language. It lets you work with as much data as you want with relatively small code if you use these forms, these idiomatic forms of iteration. And then at the end, because you have a sum over an integer, and we have a double divided by an integer, we do return a double. Our second routine, the print grades routine, is even simpler. Again, same setup. We have how many that we want to process. We pass in the grades. We have our counting variable internally to the procedure. Then I'm going to print, I have this many grades, and then I'm going to, with a tab separated format string, print out those grades. And again, as many as we want can be printed out. And now the logic becomes very simple. In main, rather than having embedded everything there, these can be reused time and again with different routines. In fact, they can get us an average. As you'll see, one of the homework problems, is to do an average for the weight of elephant seals. And here we've created the array. We called it grades. We could have called it data. We could have called it my grades. We pass it in with its how many parameter size. And then internally, we print the grades out. And in the second line, we figure out the average grades. All very clear. So just get used to writing simple functions in which a parameter is your array, and you have a very powerful tool set for handling large amounts of data.